A coarse metal gauze filter is fitted between the tank and pressure pump. It's designed to remove particles which are larger than 40 microns from the oil before it enters the pressure pump, and so prevent damage to the pressure pump. The oil pumps consist of two deep-toothed spur gears, which are rotating inside a close-fitting pump casing. They are fitted to and driven via the accessory housing. Oil is carried either side of the casing in the space between the gear teeth, and is made to flow as the gears rotate. The outlet side of the pressure pump is enclosed, and the restriction to flow is generated by the tolerance fit of the engine components to be lubricated. This enables a rise in system pressure. The actual oil pressure obtained will depend on the speed of the pump, the temperature of the oil, and the resistance offered by the tolerance with which the components fit each other. The capacity of the pressure pump must be such that it will supply a minimum oil pressure under its most adverse running conditions, which are those of low rotational speed and high oil inlet temperature. Because the pump is capable of supplying such a large quantity of oil under these poor conditions, under normal running conditions, the increased flow then available would tend to generate a dangerously high oil pressure. Very high oil pressures are prevented by a pressure relief valve, which is fitted across the inlet and outlet connections. This limits the maximum oil pressure in the system. When the oil pressure reaches a predetermined figure, the valve opens and sufficient oil is returned to the inlet side of the pump to control oil pressure at that figure. Although in theory the pressure relief valve maintains the oil pressure constant, regardless of engine speed or oil temperature, in practice the engine will have a range of operating pressure which is related to engine speed from idle to maximum RPM. The oil tank will usually be fitted at a higher level than the pressure pump to provide a gravity feed. When, after an engine run, the engine is stopped and the oil is hot and thin, the force of gravity will generate sufficient pressure in the pressure pump feed line to force the oil through the clearances in the pressure pump. This would result in the oil tank draining into the crankcase, and as a consequence the engine may be flooded with oil. To prevent this happening, a check valve is fitted in the outlet line to the pressure pump. This consists of a lightly sprung loaded valve which will retain the oil in the tank until the engine is started. The pressure filter is usually of the paper element type. It's fitted downstream of the pressure pump and is designed to remove very small solid particles of between 20 to 25 microns before the oil passes to the bearing surfaces. The method of manufacture, which incorporates a pleated paper element, ensures a large filtering area, and thus the capability of a reasonably good through flow. It will also protect the engine if the pressure pump breaks up. As shown here, on some filters a spring-loaded relief valve is fitted to bypass the filter element when the oil is cold, or if the element becomes blocked with dirt. The scavenge pump, or in some engines the scavenge pumps, pump the oil from the sump back to the tank. When the engine is stopped, the oil which remains in the crankcase will drain down into the sump. As the engine is started, there will be a quantity of oil which, if the pressure and scavenge pumps were equally capable, would not be removed. Therefore, in order to prevent excessive accumulation of oil in the sump, it's necessary for the scavenge pump to be of a larger capacity than the pressure pump. In practice, the scavenge pump capacity is 25% to 50% larger than that of the pressure pump. To protect the scavenge pump from being damaged by large pieces of debris which may have passed through the oil system, another coarse metal gauze filter is fitted over the oil outlet pipe within the sump. The importance of the use of oil to cool the internal components of the engine has already been emphasized. If the oil itself gets too hot, it may be unable to fulfill its task as a lubricant. To prevent the temperature of the oil rising too high, an oil cooler is introduced into the system. Older aircraft engine oil coolers are made up as a matrix or tube block, similar to a bunch of drinking straws which have been clamped together. Ram air flows through the inside of the tubes in the block. The oil is allowed to flow between the outer surfaces of the tubes, which are separated by dimples formed in their center section. The oil is spread in a thin film which flows through the inner surface of the matrix. Modern oil coolers use what is known as a stacked plate form of construction. A row of aluminium air fins is sandwiched between a base plate mounting bracket and a conductor plate, a sheet of aluminium. A turbulator plate, also made of aluminium, is placed on top of that, and another conductor plate finishes off the first layer. Subsequent layers are added until the prescribed number of oil rows are present. The oil is constrained to flow through the very small spaces formed between corrugations on the turbulator plate and the conductor plate, while the air flows through the air fins. When the engine is started from cold, the oil cooler will be full of cold, thick oil, and to force the oil through the small passages within the cooler would build up a very high oil pressure. To prevent this high oil pressure damaging the oil cooler, an anti-surge valve is fitted, which allows the oil to bypass the matrix when the oil is cold. The temperature of the oil is affected by three factors. Firstly, the amount of heat generated in the engine, which is proportional to engine power output. Secondly, the temperature of the cooling air. And thirdly, the rate at which that air flows through the oil cooler. In some light aircraft, the flow of air through the cooler is simply dependent on the forward speed of the aircraft in flight, and the airflow from the propeller whilst the aircraft is on the ground. In certain conditions of flight, where high power is used with low forward speed, for example during a climb, care must be taken to prevent overheating the oil. The aircraft flight manual will recommend climb speeds that should ensure adequate airflow over the cooling systems. Higher-powered aircraft will be fitted with shutters behind the cooler to control the flow of air through the cooler. The shutters would be closed at startup to allow the engine oil temperature to rise quickly. Remember, cold oil increases internal friction. And then be opened to maintain the temperature. In flight, the shutters will be closed off again as the temperature of the air reduces at altitude. Control of the shutters can be manual or automatic. The importance of maintaining the correct oil temperature has been explained previously in this lesson. The other parameters of the oil system which are monitored are oil pressure and oil quantity. The temperature of the oil in an aircraft piston engine may be measured at the outlet from the oil cooler or at any position between the oil tank and the inlet to the engine. On the majority of wet sump systems, the oil temperature is measured at the pressure filter housing. Most aircraft use an electrical sensor to indicate the temperature on a cockpit instrument. Temperatures in the region of 85 degrees Celsius, that's 185 degrees Fahrenheit, would be considered normal. Oil pressure is sensed at the outlet side of the engine-driven pressure pump. The pressure will depend on the size and loading of the engine, 50 to 100 pounds per square inch being a typical value. The sensor can be either electrical or a direct reading mechanical system. It is mandatory that oil temperature and oil pressure are indicated on the flight deck. Oil quantity may be shown in the cockpit, but if it is not, then there will be a facility for checking the quantity prior to flight, either by the use of a dipstick or a sight glass. Indications of oil temperature and pressure during engine operation are perhaps the most important that the pilot has to inform him of engine condition. Indications which are outside of the normal operating limits could be indicative of impending engine failure. Because aircraft engines operate at varying loads, power settings and outside air temperatures, their lubricants require differing properties. The thickness or viscosity of the oil is a very important factor. Viscosity is defined as the measure of a fluid's internal friction, or its resistance to flow. A liquid that flows freely has a low viscosity, thin oil, and one which is sluggish has a high viscosity, thick oil. The viscosity of an oil will change with changes in temperature. An increase in temperature will reduce viscosity, and vice versa. The engine's operating temperature will vary considerably, from the time when it is started from cold to when it's been running at high power for long periods of time. The oil's viscosity must stay within required limits to do its job, and the range of temperatures within which it can safely do this is called its viscosity index. There are various standards employed to determine the viscosity or thickness of oils. They all provide a datum by which differing oils can be compared. Obtaining these standards requires that we measure the time taken for a fixed quantity of oil at a given temperature to flow through an orifice or jet of a given size. There are two standards that are generally employed in aviation to indicate the viscosity of oils. These are the Society of Automotive Engineers, SAE, and the Commercial Aviation grading systems. Both systems use numbers to indicate the viscosity or the grade. The lower the viscosity number, the thinner the oil. From this diagram, it can be seen that the SAE number is generally half that of the commercial aviation system. Lighter loaded engines use a low viscosity or thin oil, whereas higher powered engines with higher loading would require a high viscosity or thick oil. As previously stated, the air temperature in which the engine operates also has an influence on the viscosity of the oil selected for use in that engine. For example, a light aircraft operating within the United Kingdom during the winter may use an 80 grade oil, and in summer it would use a 100 grade, the choice of the grade being dependent on the average ambient temperature. The use of too high a viscosity oil at too low a temperature can cause engine starting problems. Oils which have two viscosity values can be used to minimize starting problems. For instance, SAE 15W50. The W indicates that the oil is suitable for use in winter in cold climates. Oils with two viscosity values are called multigrade oils. They will have the characteristics of low viscosity at low temperatures and high viscosity at high temperatures. The type of oil used in aircraft piston engines is normally mineral-based. If the oil contains no additives, it's called a straight oil. To meet certain requirements of engine operation, additives can be mixed with the oil. These additives can take the form of antioxidants, dispersants, and oiliness agents. Oils which contain additives are called compound oils. Straight and compound oils are both identified by the viscosity numbering system, but a compound oil will have additional lettering as well as the number. Thus, a bottle or can containing a straight oil with a viscosity of 100 would have only the number 100 marked on it. But a compound oil of the same viscosity may be marked AD100, EE100 or W100. The actual lettering used varies with the oil's manufacturer. The letters AD, EE, and W all denote that the oil is an ashless dispersant oil. The W on the Aero Shell W100 oil, which is produced by Shell International, should not be confused with the W used in the grading system. Generally, straight oil is only used when running in new engines, or for specific engine installations. As we said earlier, piston engines normally use mineral-based oils. However, some engine manufacturers have trialled and approved the use of semi-synthetic oils. Indications of oil pressure and temperature give the pilot a good idea of the mechanical integrity of the engine. Of course, the pilot must then interpret these indications correctly. Aircraft which use radial and inverted engines require the pilot to have knowledge of the lubrication system even before he starts the engines. Both of these types of engines can suffer from a problem called hydraulicking. In radial and inverted engines, oil may accumulate in the cylinders at the bottom of the engine, between the piston and cylinder head after shutdown. Damage to the engine could occur on startup, as the piston, on the compression stroke, traps the incompressible oil between itself and the cylinder head. Prior to starting, these engines should be rotated through a number of cycles by use of the propeller, to ensure no hydraulic lock has occurred. You must, of course, ensure that the magnetos are off before turning the engine over. After starting an aircraft piston engine, positive engine oil pressure should be indicated within a specified time. The Piper Warrior checklist stipulates 30 seconds. If oil pressure is not indicated within the specified time, the engine must be shut down immediately and the problem investigated. If the engine is started from cold, initially the oil pressure could appear to be excessively high. This indication can be considered to be normal, as long as the pressure drops to within its normal range as the engine warms up. Correct engine operating pressures and temperatures are dependent on each other. As was stated before, as long as the oil pressure drops to normal as the engine warms up, this situation can be considered acceptable. However, if the pressure rises to dangerously high values, the engine must be stopped to prevent damage. The oil pressure should be within its operating range at the correct operating temperature. High oil temperature could cause the pressure indication to be low. If the oil pressure is too low, apparently because of associated high oil temperature, then this is probably due to the viscosity of the oil dropping below the point where the oil pressure relief valve can cope with the situation. If the engine is fitted with oil cooler shutters, then they can be opened in an attempt to lower the oil temperature. Alternatively, if oil cooler shutters are not an option, then consideration should be given to either reducing engine power or lowering the nose to increase airspeed, or even making the mixture richer. Any or all of these actions can be used to cool the engine and thus cool the oil, bringing its viscosity back up to the point where the system can cope. If the oil temperature is within its correct operating range and the oil pressure is still indicating that it's too low, then it's likely that there is either excessive clearance on the bearings due to wear, a defective pressure relief valve, or, potentially even worse, leaks from the output side of the pressure pump. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage being caused to some components through lack of lubrication. Fluctuations in pressure could be the result of either low oil levels or system faults. Small fluctuations of the oil pressure gauge needle, either side of the desired pressure, may be indicative of a sticking pressure relief valve. This would cause the pressure to first build up beyond the optimum level, then subsequently, when the pressure reached a point high enough to overcome the stiction of the valve, it would open, dropping the pressure momentarily below the correct level. Then the cycle would start again. Large fluctuations of the oil pressure gauge needle, on the other hand, will probably be caused by insufficient oil in the system. The engine may have been leaking oil, and eventually the level will drop to a point where the pressure pump cannot sustain its output. Then the pressure will drop momentarily until the pump can get some more oil, when the pressure will rise again, if only for a moment. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. If the oil pressure falls suddenly to zero, then perhaps the reasons may be a bit academic. After all, if the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage, and there is probably not a lot you can do about the problem. Nevertheless, the probable cause is either failure of the pressure pump or a total loss of oil. Coring is a condition which can occur in engines which are capable of developing very high power outputs. During the climb to height, inexperienced operators would sometimes tend to set the oil cooler shutters in a fairly open position to ensure that the oil temperature stayed cooler rather than hotter. Unfortunately, if the ambient temperature fell faster than anticipated during the climb, the oil temperature would fall lower and lower. The viscosity of the oil flowing through the oil cooler would rise, and eventually the oil would become so thick that in the front of the cooler the oil would stop flowing altogether. To the rear of the cooler, some oil would still flow, but being insulated from the cooling air by more and more stationary cold oil, it would get hotter and hotter. The instinctive reaction of the inexperienced operator to the indications would be to open the oil cooler shutters fully. But this would just cause the oil temperature to rise faster by thickening the insulating layer of cold oil in the front of the oil cooler. The correct actions to take would be to close the oil cooler shutters. If this is done soon enough, the heat of the oil in the core is passed outwards to oil in adjacent tubes in the matrix, lowering the viscosity of the oil sufficiently to start flow through the rest of the cooler, increasing the volume flow and thus eventually dropping the overall temperature of the oil contents. It should be appreciated that as the oil is used to lubricate the moving parts of the engine, it will come in contact with the combustion gases. The inlet and exhaust valves and piston rings do not have a 100% seal, and as a result some oil will be burnt, and the engine will therefore have an oil consumption rate. Oil consumption varies between engines. A typical light aircraft engine would use around 1 pint per hour, although some engine manufacturers consider 2 pints per hour to be acceptable. A consumption rate greater than the recommended limit may be an indication of engine wear. The oil contents should preferably be checked prior to flight. However, if the engine has a dry sump lubricating system, the oil tank contents should be checked immediately after the engine has stopped, realistically within a few minutes of shutdown. This ensures that the contents are recorded accurately before the oil migrates, under gravity, down into the engine sump. Large piston engines have oil tanks fitted with a check valve, usually situated underneath the oil tank, which is closed under spring pressure or alternatively by an electrically operated actuator on engine shutdown. The closing of the check valve prevents oil migration into the sump. The wet sump system requires the opposite treatment. A period of at least 15 to 20 minutes should have elapsed after engine shutdown before the contents are checked by using the dipstick in the engine sump. This concludes the lesson on lubrication. The piston engine is a heat engine. Its purpose is to convert the heat energy released by the fuel into mechanical energy and so allow it to do useful work. In the engine's general lesson, we stated that the thermal efficiency of a piston engine is at best only 25 to 28%. This means that over 70% of the heat energy released by the fuel in the engine is wasted. The exhaust gas is responsible for releasing around 40% of the heat energy. On some aircraft, some of this energy can be recovered by using it to drive a turbine-driven supercharger, which is commonly called a turbocharger. The remaining 32% of the heat energy released through burning the fuel raises the temperature of both the engine components and the oil. If this temperature increase is not controlled, it could be the cause of several problems. For instance, the oil temperature becoming too high, which would cause it to lose its lubricating properties, and, as a consequence, the engine would suffer possible structural failure of some of the components. Also, if the engine gets excessively hot, carbon deposits in the cylinder can become incandescent. The hot spots thus created can cause the mixture to ignite before the normal ignition point. This process is called pre-ignition. The combustion process can even become unstable after the mixture has been ignited at the normal point. This is called detonation or knocking. Both pre-ignition and detonation result in a loss of engine power. So far, only the problems of overheating have been discussed, but problems can also occur if the engine operates at too low a temperature. We must always remember that for two reasons, in order to obtain high values of thermal efficiency, it's required that we operate the engine at high temperatures. Firstly, low engine temperatures increase the internal friction of lubricants. It increases the viscosity of the oil. This would increase the friction horsepower within the engine, and thus reduce the brake horsepower available at the propeller. Secondly, the ability of the liquid fuel to change its state from a liquid to a vapour is reduced in a cold engine. This affects both the fuel mixture strength from cylinder to cylinder and the ability of the fuel to burn efficiently. Bearing these two factors in mind, then, it appears that to operate efficiently, the engine must operate at the highest temperature consistent with safe operation. Inevitable fluctuations in the ambient and engine internal temperatures require a cooling system to control and maintain the engine temperature at the optimum level. We examined the way in which the cylinder arrangement differed between engine types in the engine's general lesson. We said there that the cylinder arrangement was dependent on the power required from the engine and the type of cooling system which was used in the engine. The two types of cooling system used in aircraft piston engines are liquid cooling and air cooling. The liquid cooling system shown in this diagram dissipates the heat generated in the engine by pumping a liquid through passages built into the cylinders and cylinder heads. This liquid, which can be a mixture of water and antifreeze, is then passed through a radiator which is mounted in the slipstream of the propeller. This placement ensures that, even with the aircraft stationary on the ground, there is a flow of cooling air through the radiator. To enable both the size of the radiator, and therefore the amount of drag it generates, to be reduced, some engine manufacturers employ liquids which have a boiling point appreciably higher than that of water. One such liquid is ethylene glycol, a molecule of which is shown here. It's a clear, rather viscous liquid. When mixed with water in a 1:3 ratio, ethylene glycol raises the boiling point of the coolant, thereby preventing low-pressure boiling at altitude. It also provides good antifreeze properties. The use of this liquid can enable a reduction of radiator area of up to 50% in certain engines, like the Rolls-Royce Merlin or Griffon engine, which can be mounted in the Spitfire. The components of the liquid cooling system consist of an engine-driven pump, which circulates the liquid through the engine, a thermostat, which controls the coolant temperature, a header tank, which acts as a reservoir for the coolant liquid, pipes to allow the liquid to flow from the header tank to the engine block, and then from the engine to the radiator and back to the header tank. Air flowing through the radiator dissipates the heat from the coolant to the air. The standard design of air-cooled engine uses the cooling air from the propeller slipstream and the forward speed of the aircraft to transfer the heat generated in the engine directly to the air. The engine is surrounded by cowlings which reduce drag and control the flow of air around the engine. The controlled flow ensures that all parts of the engine are equally cooled, and it thus prevents overcooling of the front of the engine. The cooling system of the air-cooled engine has few moving parts, and thus the simplicity of the system makes it virtually maintenance-free. An air-cooled engine is also lighter in weight than a liquid-cooled engine of similar power. These are the two main reasons why an air-type cooling system is preferred on gasoline-powered aircraft piston engines. Nevertheless, it should be appreciated that a liquid cooling system is more efficient than an air cooling system. Liquid cooling gives better control of engine temperature and also produces less drag. To assist you in comparing the frontal area of these two types of engine, we have superimposed a representative liquid-cooled engine type over a representative air-cooled engine type. Both engines have similar power outputs. It is for these reasons that liquid cooling systems are used on the very powerful engines of high-speed aircraft. The main factors governing the efficiency of an air-cooled system are, firstly, the ambient air temperature, which can vary widely with changes in climatic conditions and altitude. Dissipation of the heat generated in the engine will be more rapid as the air temperature decreases. Secondly, the speed of the airflow passing over the cylinders, which is governed by the slipstream, and thus will vary with the speed of the aircraft. Some engine installations require that care be taken when ground running to prevent overheating, because as the aircraft is stationary, the only airflow over the engine comes from the propeller slipstream. On the type of installation where this is a problem, a fan may be fitted behind the propeller to obtain a greater airflow over the engine, as is shown in this diagram. The external surfaces of the air-cooled cylinder and the cylinder head are finned to increase the cooling area. The engine designer walks a fine line between ensuring that the pitch of the fins is such that a large fin area can be obtained, whilst ensuring that the fins are not so close that the resistance to airflow builds up pressure, which would tend to decrease the airflow and thus increase the drag. An average pitch for fins on a steel cylinder is about 4 per inch, whereas for fins machined from cast aluminium alloy, the pitch is less than 3 per inch. The fins have a thin cross-section. They may be extended at local hotspots so that their surface area increases in an attempt to produce an even temperature throughout the component, for example around the exhaust ports on the cylinder head. Baffles, which are shown here on this diagram, are air guides, which direct the airflow completely around the cylinder. They must be close-fitting and provide a seal with the inside of the cowlings, so that all the cooling airflow is directed around the cylinders. Care is taken to ensure that an even cross-sectional area is maintained, so that the airflow does not slow down and cause drag. Cowlings must be close-fitting without dents or projections which may disturb the airflow over them. Any disturbance to the designed airflow will not only increase the drag, but also decrease the cooling effect it delivers. Cowl flaps, or gills as they are sometimes called, when they are fitted to an engine like the one depicted here, are fitted to enable control of the airflow through the engine. With the cowl flaps or gills open, the air flowing over the engine cowling causes a pressure drop at the cooling air outlet, thus accelerating the heated airflow and enabling it to maintain a high speed over the cylinders. As the air flows over the cylinders, it absorbs heat and expands. This increases its speed even more. Any increase in the speed of the air mass flow through the engine creates a reactive force, which, by acting forwards, tends to negate some of the total engine drag. Wherever possible, engine components are made of materials with a high heat conductivity. Most air-cooled engines have cylinder heads which are machined from forged aluminium alloy. The cylinder heads are heated, and while they are still hot, they are screwed onto alloy steel cylinder barrels. It's common on some high-power engines to make the exhaust valve stems hollow, and to partly fill the space with sodium. At normal engine working temperatures, the sodium melts, and with every movement of the valve, the liquid sodium is projected from the hot valve face end to the cooler valve tip. This facilitates the dissipation of heat from the hot part of the valve to the cooler part. The cylinder head temperature gauge is an engine instrument designed to aid the pilot in protecting the engine against its enemy, excessive heat. The operation of the cylinder head temperature gauge is dependent on a probe, which is mounted on the engine cylinder head. This probe sends a voltage, which is proportional to the temperature of the cylinder head, to a gauge in the cockpit. The gauge in the cockpit is a millivoltmeter, which has been calibrated in either degrees Celsius or Fahrenheit. Most general aviation aircraft engines sample the cylinder head temperature of the hottest cylinder, The hottest cylinder is determined by extensive flight tests carried out by the engine manufacturers. The cooling arrangements for any particular type of engine are designed to ensure satisfactory cooling during cruising flight, when the forward speed of the aircraft should give an adequate flow of cool air. It is a fact, however, that aircraft go through many different stages of flight other than just the cruise, when the airflow pattern will differ from the cruise standard. The following information may assist the pilot in determining the best procedures to be employed when using the engine cooling system. At high power settings and low airspeed, such as those experienced at takeoff, the cowl flaps should be selected open to increase flow rate of air and so increase cooling. When selected to this position at takeoff, the protruding cowl flaps may increase drag. During a climb, when high power is being used, high temperatures are generated within the engine. Forward speed is, however, reduced, and thus airflow to the engine is also reduced. In this type of situation, the pilot should be aware of the possibility of overheating. Climbing at the best rate of climb speed for your type of aircraft is preferable to prolonged use of the best angle of climb speed. In the cruise at altitude, because the drop in air temperature at height will improve the efficiency of the cooling system, the cowl flaps may be partially closed to maintain the engine temperature. Descending can also cause problems. Engine power is reduced and thus less heat is generated. If the aircraft is put into a dive, this will increase the flow of air over the engine and increase the possibility of overcooling it. The sudden change in temperature thus caused is known as thermal shock. Thermal shock, which can cause engine components to fracture, happens most commonly in both the cylinders and the cylinder heads. Improved control of engine temperature, which would minimize the occurrence of thermal shock, is possible where cowl flaps or gills are fitted, but these items may not be available on many light aircraft. On these aircraft, the pilot can control the engine temperature by either manipulating the airspeed, the engine power, or the mixture control. In descent, the cowl flaps are closed in order to reduce the cooling effect of the airflow. It can also be beneficial to periodically apply engine power for short intervals during the descent. The length of time that high power settings are used on the ground should normally be limited, as the only cooling effect available is the propeller slipstream. This may not always be sufficient, and overheating can occur, especially on hot and high airfields. Both cylinder head temperature and oil temperature should be closely monitored during ground running. The engine oil temperature is particularly important because of the fact that engine components, such as the pistons and bearings, are cooled by the lubricating system. Prior to shutdown, the engine should be run at idle power for a short period until engine temperatures have reduced and stabilized. Shutting down whilst the engine is very hot can result in uneven cooling and possible damage through distortion of the components. This concludes the lesson on cooling. This diagram shows that the density, pressure, and temperature of the air are greatest at sea level, decreasing with altitude increase. Sea level pressure at any point on the Earth's surface is caused by the weight of air above that point. The decrease in density of the air with altitude increase is also due to the lessening of the weight of air above any specific point. Because the heat in the atmosphere is radiated from the surface of the Earth, the greater the altitude, the further away from the source of radiation, the lower will be the temperature. In order that an engine's power output can be checked in any part of the world, regardless of the ambient conditions at that place, manufacturers specify a set of standard maximum power RPM figures which are obtained on a standard day, according to sea level ISA conditions. ISA stands for International Civil Aviation Organization, or ICAO, Standard Atmosphere. From the diagram, we can see that the sea level ISA conditions can be said to exist at a temperature of plus 15 degrees Celsius, a pressure of 14.69 pounds per square inch, which is the equivalent of either 1013.25 millibars or 29.92 inches of mercury, or 1013.25 hectopascals, and a density of 1,225 grams per cubic meter. The density of the air directly affects the performance of any aircraft. A reduction in air density results in lower engine power, which directly affects the length of the takeoff, the landing run, and the rate of climb. The air density is not only affected by the altitude. The local air temperature will also have a direct effect on it. If the temperature of an airfield is higher than the ISA temperature for the airfield elevation, then the air density will be lower in value than the standard, and thus the density altitude will be higher than the airfield elevation. So, whereas pressure altitude, in aviation terms, is the indicated altitude obtained when an altimeter is set to 1013.2 millibars, or 1013.2 hectopascals, density altitude is used to describe how dense the atmosphere is in comparison to the international standard atmosphere. It is the altitude in the standard atmosphere at which the prevailing density would occur. We can either employ a navigation computer to determine the actual density altitude, or use a simple formula. The formula requires that we add to the pressure altitude 118 feet for every degree Celsius that the actual temperature is above ISA. For an example of how much influence the temperature can have on the density altitude, let's try an example. Imagine that you're fortunate enough to be taking off in a light aircraft from Calgary, in Alberta, on a nice summer day. The indicated outside air temperature is plus 33 degrees Celsius. The elevation of Calgary Airport is 3,550 feet. And the QNH on this particular day is 1013 millibars, or 1013 hectopascals, which makes our pressure altitude also 3,550 feet. The ISA temperature for that pressure altitude is approximately plus 8 degrees Celsius. So the ISA deviation is plus 25 degrees Celsius. Substituting in our formula, if we multiply the ISA deviation, plus 25, by 118, we get 2,950 feet, which we add to the pressure altitude of 3,550 feet. That makes the density altitude at Calgary Airport on this day 6,500 feet. Remember that engine performance is associated with the density altitude. The higher the density altitude, the lower the engine performance. In the engine's general lesson, we stated that obtaining the maximum power output from a piston engine depended upon us getting the maximum weight of the air-fuel mixture, or charge, into the cylinders during the induction stroke. Unfortunately, as we've just seen, as the aircraft climbs to altitude, the density of the air reduces. Because of this, we have to reduce the weight of fuel in the mixture to retain the mixture strength at an optimum figure. This, coupled with the fact that the pressure available in the atmosphere to assist the flow of mixture into the engine cylinders is reducing in the climb, means that less and less weight of fuel is fed into a normally aspirated engine as the aircraft gains altitude. The term normally aspirated, when it's used to describe an engine, infers that the air being induced into the cylinders is not artificially compressed. The problem of the power output of an engine decreasing with increase in altitude can to some extent be overcome by the use of some form of power augmentation device. This device usually takes the form of a supercharger, which allows additional air and fuel to be fed into the cylinders at altitude. This results in the weight of charge, and thus the power, being increased. The power output of each engine is specified by the manufacturer. Having said that, however, each manufacturer also gives various power outputs which may either be obtained at specific engine control settings or used for limited periods of time. Takeoff power is the maximum power the engine can develop. Its use is normally time-limited. The maximum continuous power the engine can produce is called rated power. This power is produced at a specified RPM and boost, or manifold absolute pressure. We'll talk more of manifold absolute pressure later in this lesson. The aircraft is normally flown in the cruise at a fraction of this power. The maximum altitude at which the engine can maintain rated power, with the throttle valve fully open, is termed rated altitude. The pressure within the induction manifold of a normally aspirated engine at full throttle is slightly less than atmospheric pressure. This is because of intake duct losses and the pressure loss which even an open throttle valve generates. We've already seen that the manifold pressure decreases with any increase in altitude. Engine power output of a normally aspirated engine, therefore, decreases with altitude. There is, however, one bonus which can be gained through climbing the aircraft. The ambient pressure decreases as the aircraft climbs, and it is this ambient pressure, or back pressure, which resists the escape of the waste gases from the cylinder during the exhaust stroke. It is this same pressure which dictates that the piston has to waste energy in driving those gases from the cylinder during the exhaust stroke. As a consequence of the reducing atmospheric pressure, some of the power wasted during the exhaust stroke is reduced during the climb, due to the more efficient scavenging of the cylinders, which results because of reduced back pressure with increasing altitude. In order to either increase engine power for takeoff and initial climb, and/or to maintain engine power at high altitude, the inlet manifold pressure must be raised artificially, and this is done by supercharging. Where a supercharger is used to increase the engine power output at sea level, rather than to maintain normal engine power output up to a high altitude, the engine will need to be strengthened in order to resist the high combustion pressure. This type of engine, like the one shown here, is fitted with what is called a ground-boosted supercharger. Superchargers capable of maintaining sea-level values of power up to high altitude require a control system to prevent excessive pressure being generated within the engine at low altitude. Engines with this type of control system, similar to the one shown here, are fitted with altitude-boosted superchargers. Both the Roots-type compressor and centrifugal compressors are used as superchargers on aircraft engines, although the centrifugal compressor, because of its relative simplicity and ease of manufacture, is more commonly used. Although the compressors may be driven by either internal or external means, in fact, in some installations a combination of both internally and externally driven compressors may be used. Externally driven superchargers, which are known as turbo superchargers or turbochargers for short, are driven by a turbine which is rotated by the exhaust gases. Externally driven superchargers compress the air. Internally driven superchargers are driven through gearing from the engine crankshaft. Internally driven superchargers compress the mixture. The methods of operation and control of these two types are quite different, and are dealt with separately. As we stated previously, the most commonly used compressors are the centrifugal type. Centrifugal compressors are comparatively light, able to run at high speed, will handle large quantities of air, and are both robust and reliable. A centrifugal compressor consists of two components: the impeller, which is rotated and accelerates the air, and the diffuser, which collects and directs the air into the inlet manifold. Air is drawn into the eye of the rotating impeller, which incorporates a number of radially disposed divergent vanes. Initially, by converting the mechanical energy which has been imparted to it by the impeller into kinetic energy, the air is accelerated radially outwards between the vanes. And, as the cross-section of its path through the vanes increases, it decelerates, and some of the kinetic energy gained is converted into pressure energy. The proportion of pressure gained in the impeller depends on the impeller's diameter. The larger the diameter, the greater the pressure gain. Its speed of rotation, the faster the impeller rotates, the greater the pressure gain. And the shape of the vanes. The air leaves the impeller with considerable tangential and radial velocity and passes into the diffuser. The diffuser can either be in the form of a divergent passage, as is shown here, or in larger units it may take the form of a series of vanes set within the volute casing, which simultaneously decrease the velocity and increase the pressure of the passing air. We learnt in the introductory lesson that the action of compressing the air increases its temperature, and thus reduces some of the increase in density which would otherwise result from the increased pressure. This loss of density may be partially recovered, either by passing the air through a heat exchanger, sometimes called an intercooler, or by spraying the fuel from the carburetor into the eye of the impeller, so that vaporization will reduce the air temperature. At any given speed of rotation, a centrifugal compressor increases the pressure of air which passes through the impeller in a definite ratio. Physical constraints limit the speed of rotation and size of an impeller, and so limit the pressure rise, or pressure ratio, which can be gained from it. Consequently, the power output and the maximum operating altitude of the engine to which it is fitted are also limited. Pressure ratios between 1.5 to 1 to 4 to 1 are generally obtainable from a centrifugal compressor incorporating a single impeller. This is known as a single-stage supercharger. If any further compression was needed, it would require that 2 or 3 impellers be installed in series, in what is known as 2-stage or 3-stage superchargers, respectively. Most engines which are fitted with a supercharger will also be fitted with a variable pitch propeller. This will be controlled by a constant speed unit. The RPM of the engine is therefore controlled by the propeller pitch lever. To accurately set the power and also prevent the engine from being overboosted, the pilot must have some indication of the amount of pressure he is allowing into the engine. This pressure is known as the intake or induction manifold pressure, and is indicated to the pilot on either a boost pressure gauge or a manifold absolute pressure gauge. In many older engines, particularly British supercharged engines, the pressure in the induction manifold, relative to sea level standard pressure, is called boost pressure. The boost pressure gauge is calibrated in pounds per square inch above or below standard sea level atmospheric pressure, which is indicated on the dial by the 0 position. Thus, if the boost gauge is indicating -3 pounds per square inch of boost, the absolute pressure in the induction manifold system would be 14.7 psi minus 3 psi, which is equal to 11.7 psi. Similarly, if there is +4 psi boost indicated, then the absolute pressure in the induction manifold system would be 18.7 psi. Current practice is to use the American method of measuring induction system pressure, known as manifold absolute pressure, or MAP. The manifold absolute pressure gauge indicates the absolute pressure in inches of mercury. When the atmospheric pressure is 14.7 pounds per square inch, it will support a column of mercury 29.92 inches high. Therefore, a boost pressure of 0 psi is the equivalent of an induction manifold pressure of 29.92 inches of mercury. A comparison of the units of manifold absolute pressure and boost pressure will show that 2 inches of mercury is approximately equal to 1 pound of boost. Externally driven superchargers are powered by the energy of the engine exhaust gases and are generally known as turbo superchargers or turbochargers. This simplified diagram shows a turbocharger consisting of a turbine wheel and an impeller fitted on a common rotor shaft. The bearings of the shaft are lubricated by oil from the engine. The turbine is driven by the exhaust system, and the compressor is connected to the induction manifold system. The turbocharger need not necessarily be an integral part of the engine. It can be mounted either on the engine or on the fireproof bulkhead, and situated remote from combustible fluid lines in the engine bay. Exhaust gases pass through nozzles and are guided onto vanes on the turbine wheel, causing it to rotate. The gases then pass between the vanes and are exhausted overboard. As more exhaust is passed over the turbine, it will accelerate, therefore driving the impeller faster. Thus, the pressure ratio of the compressor and its output increases as the turbine speed increases. This diagram shows a comparison of the power curves of a normally aspirated engine and a turbocharged engine. Notice that the power output of both types of system falls off as the aircraft climbs, but that the normally aspirated engine output falls off more rapidly. Note also that after critical altitude has been exceeded, critical altitude being the altitude above which the selected manifold pressure can no longer be maintained, the power output of the turbocharged engine drops off at the same rate as that of the normally aspirated engine. For any particular power output, the turbocharger must deliver a constant mass of air to the engine in a given time, and since the density of air decreases with altitude, the impeller rotates faster as the aircraft climbs to compensate for the reduction in density, and so maintains the selected manifold pressure. Some form of control over compressor output must be provided, and this is done by varying the quantity of exhaust gas passing to the turbine to vary its speed and that of the compressor. The simplest form of turbine control is that which has the turbine bypassed by a pipe which contains a fixed orifice. This ensures that a proportion of the exhaust gases will always drive the turbine, and the manifold pressure is controlled directly by the throttle valve. With a fixed orifice system, it must be borne in mind that as the throttle is opened to gain more manifold pressure, the increased exhaust gases which are produced as a result will cause the turbine speed to increase in response. This will trigger a further increase in charge weight, which will generate a further increase of exhaust system pressure. With this type of simple system, this chain reaction, which can be brought about by rapid movement of the throttle, may induce the occurrence of overboosting. An alternative to the simple fixed orifice system has the turbine bypass fitted with a valve known as a wastegate. The wastegate regulates the amount of exhaust gas which passes through the turbine and thus controls its speed. When the wastegate is fully open, almost all of the exhaust gases pass directly to atmosphere. We have already stated that the critical altitude is the altitude above which the selected boost or manifold pressure can no longer be maintained. As the aircraft climbs, to maintain the required pressure in the inlet manifold, the turbine and the compressor must be driven faster and faster. To ensure that this happens, the wastegate progressively closes. Once the wastegate is fully closed, which happens at the critical altitude for that engine and turbocharger, if the aircraft continues to climb, the manifold pressure can no longer be maintained above that altitude. The wastegate may be controlled manually by the pilot, but most turbocharger systems have an automatic control fitted to prevent overboosting of the engine. In an automatic control system, the wastegate is mechanically connected to a piston situated within an actuator. The position of the piston depends on the opposing forces of a spring and engine oil pressure. Spring force tends to open the wastegate, and oil pressure tends to close it. Thus, oil pressure in the actuator regulates the position of the wastegate according to engine requirements. Various controllers may be used to vary the wastegate actuator oil pressure. These are some of the types of controller which can be used. Absolute pressure controller, variable pressure controller, differential pressure controller, density controller, rate of change controller, pressure ratio controller. We will initially concentrate on the absolute pressure controller. Earlier we mentioned that some simple turbocharger systems use an absolute pressure controller. The absolute pressure controller is designed to limit compressor output to a preset value by means of a wastegate actuator. A diagram of this type of controller is shown here. The absolute pressure controller uses an aneroid capsule, which is sensitive to compressor outlet pressure, to control the oil bleed away from the wastegate actuator, thereby controlling the wastegate position to maintain the required compressor outlet pressure. The throttle valve is then responsible for controlling manifold pressure. At low power settings, full oil pressure is applied to the wastegate actuator, which closes the wastegate and diverts all the exhaust gases through the turbine to maintain the compressor outlet pressure at the designed value. The oil, which is used to move the piston in the wastegate actuator, is taken directly from the engine lubrication system. This oil is also used to cool and lubricate the turbocharger bearings. When the throttle is opened, the engine RPM is increased. This produces an increase of exhaust gases, which increases the supercharger turbine and compressor speed, and this results in an increase in compressor outlet pressure. As the predetermined outlet pressure is approached, the absolute pressure controller capsule is contracted, which opens the bleed valve to bleed oil away from the wastegate actuator. This allows the actuator spring to open the wastegate and divert some of the exhaust gases away from the supercharger turbine. The supercharger speed is reduced, and supercharger outlet pressure is maintained within the predetermined limit. As the aircraft climbs to altitude, the air density decreases, and compressor outlet pressure reduces. This causes the APC capsule to expand and close off the wastegate actuator oil pressure bleed valve. With increasing actuator oil pressure, the wastegate is progressively closed, and more exhaust gases are directed to the turbocharger turbine. This increases both the turbocharger RPM and compressor delivery pressure, thereby maintaining the selected manifold pressure. Eventually, the wastegate will be fully closed, and the aircraft has reached critical altitude. Above this height, both manifold pressure and engine power output will drop off, despite the turbocharger operating at full speed. Coarse use of the throttle may cause a phenomenon called throttle sensitivity to occur. Throttle sensitivity is a result of a chain of events which can occur as a result of change of throttle position. Let's imagine what might happen if the pilot opens the throttle in a simple system with an absolute pressure controller like the one just described. Initially, the inlet manifold pressure will rise. The absolute pressure controller will sense a drop in compressor output pressure, and the aneroid capsule will expand to close the oil bleed valve, increasing the oil pressure in the wastegate actuator. the wastegate will close in response. The new wastegate position diverts more exhaust gas to the turbine, which accelerates. Compressor output rises in response to the increased turbine speed. As a result, the inlet manifold pressure will rise again, and so on. The result is that the turbocharged engine's boost, or manifold absolute pressure setting, will require frequent adjustment, particularly if the pilot moves the throttle valve quickly, not waiting for the system to stabilize before making further adjustments to the throttle. The use of a differential pressure controller will help to control these unstable conditions, which are sometimes called bootstrapping. Bootstrapping occurs during part throttle operation, and it's an indication of unregulated power change that results in a continual drift of boost or manifold absolute pressure. It's an undesirable cycle of turbocharging events, causing the boost or manifold absolute pressure to drift in an attempt to reach a state of equilibrium. This diagram shows the differential pressure controller and a density controller being used to control the position of the wastegate. This is a more sophisticated system than that which simply uses the absolute pressure controller. The differential pressure controller is used to reduce the compressor output pressure during partial throttle operation. The differential pressure controller senses the pressure drop across the throttle. If a lower than maximum manifold pressure is required, the differential pressure controller will adjust the wastegate position to maintain a differential pressure of approximately 2 inches of mercury between the compressor outlet, deck pressure, and the inlet manifold. As previously stated, the differential pressure controller is used to control compressor output pressure during partial throttle settings. At full throttle settings, it would have reached its maximum controlling limit, and will no longer be capable of controlling wastegate operation. As a result, a density controller is usually installed as a safety backup to the differential pressure controller. The density controller limits the maximum manifold pressure and maintains compressor outlet density to that required for full power at full throttle settings up to critical altitude. The density controller is fitted with a capsule filled with dry nitrogen, which is sensitive to both compressor outlet pressure and temperature, and therefore its density. The capsule increases the compressor outlet pressure to compensate for the drop in charge density which results from a temperature increase caused by the compressor working harder as the aircraft climbs. Having a density controller will ensure that maximum available density will increase up to critical altitude. By so doing, the density controller will reduce the losses normally associated with charge temperature increase, and thus density decrease, which would otherwise occur as the aircraft climbs. Either the density controller or the differential pressure controller will be in use and controlling the wastegate position at any one moment. Another type of single controller system is the variable pressure controller, which is similar to the absolute pressure controller, but has a cam mechanism interconnected to the throttle linkage. The cam adjusts the setting of the oil bleed valve as throttle position is varied, thereby controlling wastegate position to provide a manifold pressure relevant to a given throttle position. The controller capsule will continue to adjust for changes in altitude. Some engines have the oil pressure control for the wastegate actuator managed by 3 controllers, all of which sense compressor outlet pressure. The 3 controllers are an absolute pressure controller, a rate of change controller, and a pressure ratio controller. We've already described the operation of the absolute pressure controller. Here we'll concentrate on the rate of change controller and the pressure ratio controller. The rate of change controller will govern the rate of change of MAP when the throttle is open rapidly. One particular type of controller limits the rate of change to 6.4 inches of mercury per second. Limiting the rate of change should prevent overboosting the engine as a result of the momentum of the compressor-turbine combination as it accelerates. At high altitudes, the compressor has to use its maximum output to compensate for the low ambient air pressure. Because of this, the temperature of the compressor output is high, often high enough to cause detonation to occur in the cylinders. Typically, the pressure ratio controller will control the compressor delivery pressure at a ratio of approximately 2.2 times the ambient pressure, and will therefore control the temperature of the charge. The pressure ratio controller usually comes into operation above the critical altitude. Additional safety features may be built into some systems. These can take the form of overboost warning lights and an overboost relief valve. If, despite the overboost warning light, the maximum boost is exceeded, then the overboost relief valve will open and relieve compressor outlet pressure to atmosphere. Maintaining a constant pressure at the outlet of the turbocharger up to critical altitude depends on being able to keep increasing the speed of the turbine as the aircraft climbs. We've already stated that this is done by progressively closing the wastegate and diverting an increasing amount of exhaust gas through the turbine. The position of the wastegate is therefore an important factor governing the performance of the engine. The position of the wastegate throughout the running of an engine from start to above critical altitude, the engine power output, the turbine speed, and the manifold pressure are all shown in this graph. Prior to start, the wastegate must be open to allow the free flow of exhaust gases to atmosphere. Otherwise, the engine would be very difficult, if not impossible, to start. To achieve this, the spring in the wastegate actuator forces it fully open. Immediately after start, there is probably not enough exhaust gas to spin the turbine fast enough to create the pressure required by the system designer at the outlet of the compressor. The aneroid capsule in the absolute pressure controller will therefore be expanded, closing the bleed valve, trapping oil within the wastegate actuator, causing its piston to close the wastegate fully. As the throttle is opened, sufficient exhaust gas will be produced by the engine to turn the turbine fast enough to enable the compressor to achieve more than the required pressure at its outlet. This increased pressure is sensed in the aneroid capsule in the absolute pressure controller, and oil is released through the bleed valve from within the wastegate actuator, thus allowing its internal spring to start opening the wastegate. The wastegate will continue to open as the throttle is opened, until at full throttle at sea level ISA pressure, it is almost fully open. The wastegate has to be able to open a little further than the position it assumes on an ISA day at sea level to cater for those days when the ambient pressure is greater than ISA. Without the ability to open further, there would be no way to reduce the turbine speed and thus maintain the compressor outlet pressure within limits on those high ambient pressure days. From the moment of takeoff, and throughout the climb, the pressure at the compressor inlet falls, causing its outlet pressure to fall also. This drop in outlet pressure is signalled to the aneroid capsule in the absolute pressure controller, which progressively closes the bleed valve, increasing the pressure of the oil in the wastegate actuator, causing it to gradually close the wastegate. Eventually, an altitude will be reached where the wastegate will be fully shut, and no more increase in turbine speed is possible. This altitude is termed the critical altitude. From now on in the climb, the outlet pressure of the compressor will fall, and the inlet manifold pressure and engine power output will fall in sympathy. Of course, the engine power output will have been decreasing with every foot of the climb from the moment of takeoff. This is typical of a turbocharged engine, but as we saw earlier, after critical altitude, the rate of decrease gets greater, approximating that of a normally aspirated engine. As you can see from this graph, the power developed by the normally aspirated engine is at a maximum at sea level, and progressively decreases as altitude is increased. The power developed by an otherwise identical but supercharged engine at the same RPM and manifold pressure is less than that of the normally aspirated engine at sea level. This power loss represents the power required to drive the supercharger. However, as height is increased, the power developed by the supercharged engine at constant throttle settings increases as a result of the decreased temperature of the atmosphere. The decreasing temperature causes the density of the air to fall less rapidly than it otherwise would if the temperature stayed constant or even increased, and thus a greater weight of air is pumped into the cylinders for the same manifold pressure. The decrease in air pressure experienced in the climb also causes less back pressure on the exhaust, thus improving scavenging of the cylinders and the efficiency of the engine. Internally driven superchargers are generally used on medium and high-powered piston engines, approximately 250 brake horsepower and above. They're fitted downstream of the throttle valve. Just as with the externally driven turbochargers, the most common form of compressor used in the internally driven supercharger is the centrifugal compressor. The compressor impeller is made as light as possible from magnesium or aluminium high-strength alloy. A shaft, splined into the rear of the crankshaft, provides the initial drive to the supercharger impeller. Notwithstanding the lightness of the compressor impeller, because of the high rotational speeds at which it operates, up to 25,000 RPM in some cases, the inertial forces generated during engine acceleration and deceleration are huge. To minimize the inertia stresses in the impeller drive, some of the systems incorporate a spring drive unit. This transmits the drive through intermediate gears to the impeller pinion, and limits the high torque impulses transmitted to the supercharger impeller during high rates of propeller engine acceleration or deceleration. Historically, the superchargers of some high-powered engines have been driven at 2 speeds, in order to save power at low altitudes. The low speed, or MS, moderate speed gearing, is used at low altitudes where the atmosphere is relatively thick, and the high speed, or FS, full speed gearing, used at high altitudes where more effort is required to compress a comparable weight of mixture. This graph compares the outputs of 3 engines. The first is normally aspirated. The second has a single-speed supercharger, and the third has a 2-speed supercharger. Some high-powered superchargers have also been fitted with 2 impellers working in series, in order to raise the overall compression ratio. Notice the addition of an intercooler after the second stage of compression. When used in general aviation aircraft, internally driven superchargers normally employ a single impeller, driven at a fixed speed relative to the crankshaft, usually between 8:1 and 12:1. This type of supercharger is capable of maintaining sea-level manifold pressure up to an altitude of between 5 and 10,000 feet, at rated power settings, depending on the gear ratio. Since a supercharger is designed to compress air and provide sea-level pressure or greater in the induction manifold when atmospheric pressure is low, excessive manifold pressure could be produced when atmospheric pressure increases, especially in a rapid descent like the one depicted on screen here. It's necessary, therefore, to restrict full throttle opening when the aircraft is operating at heights below full throttle height, and, to relieve the workload on the pilot, this is often done automatically. There are 2 controls that affect the pressure developed by the supercharger. They are the throttle lever position, within the limits imposed by full throttle height, a term which will be explained shortly, determines the boost pressure that is delivered by the supercharger. The throttle is, in effect, a boost selection lever, and, together with the propeller control lever, determines the power output of the engine. Almost without exception, variable pitch propellers are installed on supercharged aircraft engines. A variable pitch propeller allows the propeller blade angles to be adjusted in flight between fine and coarse limits. This results in the RPM of the engine increasing or decreasing. Thus, the propeller pitch control lever can be said to be an engine speed control, and as the supercharger impeller is driven by gears from the crankshaft, any change in engine speed will result in a corresponding change in the speed of the rotation of the compressor impeller. Having said this, if the engine is fitted with an automatic boost control unit, then the boost pressure reading will essentially remain constant at whatever is set by the throttle lever, while the engine RPM changes independently. Two-speed superchargers may have automatic or manual gear selection, which allows the use of moderate gear for low altitudes and a higher gear for greater altitudes. Where manual selection is used, the pilot is provided with either a mechanical push-pull selector or a two-position electrical switch. The selector or switch will be marked MS for moderately supercharged and FS for fully supercharged. While the engine is operating at sea level, the throttle valve of a supercharged engine must be partially closed, so as to restrict manifold pressure and prevent excessive cylinder pressure. Imagine the aircraft climbing with rated power set. To obtain rated power, we must set both rated RPM and rated boost. At the start of the climb, the throttle valve would be only partially opened, but as the aircraft climbs, the throttle valve must be progressively opened, either manually or automatically, to maintain the required boost or manifold pressure. Eventually, a height is reached where the throttle valve is fully open, and this is known as full throttle height. Above this height, power will fall off in a similar manner to the way it does with the normally aspirated engine. The full throttle height at rated power settings, that is rated RPM and rated boost, is known as rated altitude. Since the output of the supercharger depends on the speed of rotation of the impeller, each power setting will have a different full throttle height, according to the engine RPM and boost or manifold pressure used. For instance, if the aircraft is climbed with rated RPM, but less than rated boost, then full throttle height at this power setting will occur at a greater altitude than when climbing at rated power, as is illustrated here. If, on the other hand, the aircraft climbs with rated boost set, but with less than rated RPM, full throttle height will occur at a lower altitude than when climbing at rated power, as shown here. In summary, then, the effect of reducing engine RPM, and hence supercharger rotational speed, while maintaining the selected boost pressure, would be to reduce the full throttle height. The reduction in full throttle height happens because the reduced engine, and thus compressor speed, reduces the compressor output. In turn, this makes it necessary to open the throttle valve by a greater amount sooner than would otherwise be the case, in order to achieve the same manifold pressure. The supercharger is designed to maintain a selected manifold pressure. To do this at altitude, the impeller must be driven at a high speed, because of the considerable reduction in atmospheric pressure with increased height. Therefore, at low altitudes where the air is much more dense, the supercharger produces too much pressure. Consequently, to avoid severe detonation and mechanical stresses due to excessively high combustion pressure, the delivery pressure must be restricted by only partially opening the throttle valve. As the aircraft climbs, the throttle valve must be progressively opened further to maintain the selected boost pressure. To relieve the pilot of the responsibility of constantly varying the position of the throttle lever during the climb or descent, the boost pressure is kept constant automatically by the automatic boost control unit, a diagram of which is shown here. The automatic boost control unit is situated between the throttle lever in the cockpit and the throttle valve on the carburetor. The automatic boost control unit contains an aneroid capsule, which is sensitive to changes of inlet manifold pressure. The position of the carburetor throttle valve can be set by moving the pilot's throttle lever. A landed valve connected to the underside of the aneroid capsule is also positioned by movement of the pilot's throttle lever. Engine oil pressure is directed by the landed valve to either side of a servo piston, which adjusts the position of the carburetor throttle valve in response to changes in manifold pressure. If the manifold pressure exceeds the figure selected by the pilot, as it may do in a descent, then the aneroid capsule contracts, lifting the landed valve to allow pressure oil to be fed to the top of the servo piston, which in turn closes off the throttle valve a sufficient amount to bring the manifold pressure back to the selected figure. If, on the other hand, the manifold pressure drops below the selected figure, as it would in an extended climb, then the aneroid capsule expands, lowering the landed valve to allow oil pressure to be fed underneath the servo piston. This opens the throttle valve to allow more air from the supercharger into the manifold, thus raising the pressure back to that which was selected. We've already seen how the power of both a normally aspirated and a turbocharged engine decreases with increase of altitude. The effect of altitude change on a supercharged engine is totally different. This diagram shows how the power output of an internally supercharged engine increases with increase of altitude, up to full throttle height. This happens because of the different effect that exhaust back pressure has on each type of supercharger. Whereas with an internally supercharged engine, the exhaust back pressure reduces as the aircraft climbs, and thus absorbs less power in the exhaust stroke, because the wastegate of a turbocharger restricts the escape of the exhaust more and more as the aircraft climbs, in order to drive the turbine faster, its exhaust back pressure increases with altitude. As part of the type certificate information, the manufacturer states the engine limitations for each particular aircraft, which include the maximum static or reference RPM. This gives a baseline figure against which the engine's future condition may be checked. A note of the reference RPM is made and placarded somewhere convenient in the cockpit, for example on the relevant RPM gauge. Supercharged engines will normally run at a constant speed at high power settings, under the influence of the variable pitch propeller, and small changes in power will not affect the engine speed. As a consequence, it's impossible to check the power output from only the evidence of the RPM. The procedure for checking that an engine's power output is correct is as follows. Initially, the engine must be run until normal temperatures and pressures are obtained. It must then be opened up to maximum takeoff manifold pressure, or boost pressure. The power must then be decreased until a fall in engine RPM occurs. The reduction of RPM is indicative of the propeller blades being on their fine pitch stops. The engine must then be throttled back further to obtain the manifold pressure quoted by the manufacturer, which in our instance we'll say is 35 inches of mercury. Once the prescribed manifold pressure has been obtained, the engine speed should be within 50 RPM of the engine reference RPM. Once the reference RPM has been established, it remains fairly constant. Any deviation from it would probably indicate some form of engine malfunction. A new reference RPM will have to be established every time a major engine component, such as a magneto, is changed. Before an engine is started, its boost pressure gauge, or manifold absolute pressure gauge, depending on whether the system is British or American, supercharged or turbocharged, will show approximately ambient atmospheric pressure. At exactly sea level pressure on an ISA day, this will mean that a reading of 29.92 inches of mercury on a manifold absolute pressure gauge, or 0 boost on a boost pressure gauge, will be indicated. Because the gauge is effectively reading atmospheric pressure from the manifold of an engine that is stopped, with an increase of airfield altitude, the gauge reading will of course fall. And conversely, if the airfield ambient pressure is above ISA sea level pressure, then the gauge reading will rise to that level. The gauge reading at this point, that is, before engine start, is known as static boost, and a note should be taken of it in order that a check of engine power output can be made. As the engine is started, the pressure in the inlet manifold will decrease to read below the static boost figure. It will probably not begin to rise as the throttle is opened until about 1600 or 1700 RPM is established. With maximum RPM selected, that is the propeller on the fine pitch stop, as the throttle is progressively opened, the inlet manifold pressure should regain the static boost figure at the reference RPM, plus or minus a small tolerance of, say, 50 RPM. The reference RPM will vary with different models of engine, but would on average be 2500 RPM. Any result which is outside tolerance may be the result of a cylinder down on power, the ignition system malfunctioning, a carburetor maladjustment, or even an improperly set propeller low-pitch stop. When making comparisons between turbochargers and internal superchargers, it's inevitable that the question of which is best is asked. If it was just a matter of added performance at ground level for a given cost, then the turbocharger would probably win. There are other considerations to be taken into account, however. First of all, do we only want the added performance at ground level? Unavoidably, in the case of an aircraft, the answer must be no, in which case the internal supercharger, with its ability to increase engine power with aircraft altitude, must be the favourite choice. Secondly, do we require that the response to throttle opening be instant? If the answer to this is yes, then once again the internal supercharger wins hands down. The aircraft engine turbocharger, for all that it is the cheaper option, cannot, with present-day technology, respond to rapid throttle opening without suffering from the phenomenon known as turbo lag. Turbo lag results partly from the inertia of the turbocharger and partly from the time taken by the absolute pressure controller to respond to low compressor output signals. It also takes time for the wastegate actuator to react and close the wastegate. Thus, there is an inevitable delay between asking for power and getting it. Here is a table which illustrates the differences between the supercharger and the turbocharger. This concludes the lesson on power augmentation. In this lesson, you'll learn about propellers, their function and operation. Although we will, of necessity, very occasionally make mention of the aerodynamics of propellers, it is important you be aware that this is not a lesson on the aerodynamics of propellers. Propeller aerodynamics are dealt with in the subject Principles of Flight. The purpose of a propeller is to provide thrust to drive the aircraft forwards through the air. This is achieved by accelerating a comparatively large mass of air rearwards, thereby producing forward thrust. A propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft which is driven, either directly or indirectly, by the engine. The hub and the blades are thus spun round by the propeller shaft, and act rather like wings, which by rotating would generate lift, or in this case, thrust. In order to be able to explain how a propeller works, it's necessary that we use a certain amount of terminology. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section, whose chord line passes from the center of the leading edge radius to the trailing edge. The cambered side of the blade is called the back, while the undercambered side is termed the thrust face. Where the section of the blade becomes round at the root area is termed the blade shank, while the base of the blade is called the blade butt. The propeller blade is set into its hub so that its chord line forms an angle with the plane of rotation of the whole propeller. This is called either the pitch or blade angle. The theoretical distance, ignoring slippage, that a propeller or propeller blade moves forwards when the propeller shaft has completed one rotation is called the geometric pitch. All propellers, however, lose a certain amount of efficiency due to aerodynamic and compressibility losses. As a result, the geometric pitch can never be achieved. The actual distance that the propeller moves forward during one revolution is called the effective pitch. The efficiency loss, that is, the difference between geometric pitch and effective pitch, is known as slip. The efficiency achieved will usually be in the range of 80 to 90%, and can be found by using this formula. The path of the propeller blade through the air, which describes a helix, determines the direction from which it will receive its relative airflow. This helical path is the resultant of the propeller blade rotational velocity and the aircraft forward velocity. The angle between the relative airflow, the actual path the blade describes through the air, and the chord line of the blade is called the angle of attack. The angle of attack is kept quite small, usually between 2 to 4 degrees. As the blade rotates at this small, positive angle of attack, a thrust force is generated, very similar to the way in which lift is generated on a wing. Because the rotational velocity of any point on a propeller blade increases with increasing distance from the center of the hub, so the magnitude of the thrust generated at any point along the blade would also increase with this distance, if the pitch of the blade remained constant along its entire length. If the blade pitch remained constant along the length of the propeller blade, the increase in force developed by the outer part of the blade, compared with that developed at the slower-moving blade root, would tend to bend the blade as depicted here. The angle of attack depends on blade angle, the rotational speed of the propeller, and the forward speed of the aircraft. To keep the angle of attack within necessary limits along the length of the blade, we therefore reduce the blade pitch from root to tip. This has the effect, when the aircraft is in flight, with the propeller rotating at its designed operating RPM, of maintaining a fairly constant thrust force along the length of the blade. We've just seen that a propeller receives its relative airflow from a direction which is governed by the aircraft's true airspeed in the direction of flight, and its own rotational velocity in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line is set at an angle to the plane of rotation, which, as we've already seen, forms the blade angle or the propeller pitch. From this animation, it can be seen that an increase in true airspeed will reduce the angle of attack, whereas an increase in rotational velocity, or RPM, will increase it. At high true airspeed and low propeller RPM, for instance with the aircraft in a power-off dive, it's possible to reduce the angle of attack to 0. While at low true airspeed and high RPM, for instance in the climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM, as is shown in this diagram. The propeller designer will attempt to ensure that peak efficiency is achieved at cruise true airspeed and cruise RPM. When a fixed-pitch propeller is being driven by a piston engine, the RPM is dependent on both the power setting, throttle position, selected by the pilot, and the true airspeed of the aircraft. It would be possible to overspeed the engine in a dive if the throttle was not closed. Conversely, with the aircraft stationary on the ground, it may not be possible to achieve rated RPM with the throttle fully open. Because of all of the disadvantages of the fixed-pitch propeller that we have just mentioned, advanced piston engine aircraft are fitted with variable pitch, constant speed propellers. This type of propeller is able to operate efficiently over a wide range of airspeeds. The power setting of a piston engine is defined by a combination of manifold pressure and engine RPM. Where both a separate power lever and a propeller RPM control are provided, it's possible to vary one of these parameters while leaving the other to remain constant, so optimizing the operation of the engine-propeller combination to give the best efficiency and fuel economy, while reducing the engine wear and tear to a minimum. In order to achieve this, a variable pitch propeller is used. The system changes the pitch angle of the propeller blade to vary the load on the engine, thereby maintaining the selected RPM of the engine-propeller combination independent of manifold pressure, provided that the propeller is operating between its fine and coarse pitch stops. The fine and coarse pitch stops may be fitted internally or externally, depending on the make of the propeller. Once an RPM has been selected, a control unit, either a constant speed unit or propeller control unit, will automatically vary the propeller blade pitch angle, and therefore its angle of attack to the prevailing relative airflow, in order to maintain the selected RPM despite variations in airspeed and manifold pressure. Variable pitch propellers may also have a reverse pitch and/or feathering function, the advantages of which will be discussed later in this lesson. This animation shows that under normal propeller control conditions, it's possible to provide a range of propeller pitch angles ranging from max coarse, cruise, all the way through to reverse pitch. The alpha, or constant speed range, is used for normal flight. It includes all pitch angles from flight fine through to max coarse, while the beta, or ground range, includes pitch angles between flight fine and maximum reverse. The feather position is not included in either range, and is used for emergency conditions only. In the event of engine failure, the propeller blades will be moved directly to this position to prevent windmilling. There are no pitch angles available between max coarse and feather. The method of control within the alpha and beta ranges, and the means of achieving the propeller feather position, will be discussed progressively throughout this lesson. Varying the pitch of a propeller throws up two basic problems, one of blade actuation and one of pitch control. We will initially examine the problem of blade actuation. The issue of pitch control will be covered later in this lesson. Although mechanically or electrically actuated pitch change mechanisms are in use, the hydraulic method is the most commonly used. The system utilizes oil from the engine or reduction gearbox lubrication system as the source of hydraulic pressure. In this system, the pitch change mechanism is operated by a piston moving under the influence of the oil pressure. Use the up and down arrows on your keyboard to change the pitch of the blades on this propeller. Hydraulic pitch change mechanisms can be one of two types, single-acting or double-acting. A single-acting propeller has oil pressure applied to only one side of the piston. The return movement of the piston requires the force of a spring, or sometimes compressed gas. A double-acting propeller has oil pressure applied to either side of the piston, in order to move the propeller between the two extremes of fine and coarse pitch. Whichever type is used, the flow of oil to and from the actuating piston is controlled by a propeller governor. Dependent on the propeller manufacturer, The governor may also be known as a constant speed unit or propeller control unit. In addition to controlling the propeller pitch angle, the unit normally incorporates a small oil pump, which increases the oil pressure to the value required for system operation. A single acting propeller is constructed basically like any other variable pitch propeller, in that the blades are arranged round a central, engine-driven hub with the cylindrical hydraulic pitch change mechanism mounted at the front. The pitch change cylinder, or dome, contains a movable piston which is activated by boosted engine oil pressure. Movement of the piston will rotate the propeller blades towards either coarse or fine pitch. Typically, rotation is accomplished by a mechanical linkage attached to the rear of the piston, which operates an actuating pin machined on the butt of each blade. The actuating pin is offset, in order that it can impart the correct range of angular motion. Generally, blade rotation towards coarse pitch is induced by an internal spring or gas pressure, and or counterweights attached to the blade roots. Most single-acting propellers, however, will utilize both a spring and counterweights. As we said earlier, some systems may use compressed gas instead of the spring. In feathering-type propellers, the spring has a dual function. It assists the counterweights in driving the propeller blades towards coarse pitch, and, when selected by the pilot, it actuates the blades into the feathered position, when engine RPM is low and there is insufficient centrifugal force acting on the counterweights. The constant speed unit, or CSU, incorporates a valve, which, because it has lands or grooves cut into the operating portion of its stem, is called a landed valve. This landed valve controls the flow of oil to and from the propeller actuating, or pitch change cylinder. A speeder spring, acting above the valve, tends to force the valve downwards, while a set of flyweights, driven by the engine, oppose the spring and act to lift the valve. An input from the pilot's RPM lever, or propeller condition lever, will adjust the setting of the speeder spring, selecting the RPM, which the CSU then automatically maintains. In order that it can respond to the various demands made by the pilot regarding the propeller RPM, the constant speed unit controls the oil flow to the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed in the system, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will allow oil to drain back into the engine system as the piston is moved under the force of the spring, coarsening the blade pitch, causing an RPM decrease. One type of double-acting mechanism used on larger propellers, like the one shown here, achieves control of blade pitch angle by means of a hydraulically actuated piston connected to a cam slot, which rotates a bevel gear. The bevel gear engages with and drives other bevel gears located at the butt of each blade. Oil flow to either side of the piston is controlled by a propeller control unit. Alternatively, the type of control system shown here has a similar pitch change mechanism to the single-acting propeller. Like the single-acting propeller, its pitch change mechanism is also mounted towards the front of the hub, and the cylinder also contains a hydraulic piston. However, in the double-acting system, this piston will have hydraulic pressure directed to either side of it. Fine pitch oil is sent to one side of the piston, or coarse pitch oil is sent to the other. This eliminates the need for coarse pitch springs or gas pressure, and, with the exception of some larger propellers, the assistance of centrifugal counterweights. The double-acting propellers controller will respond to the various demands made by the pilot regarding the propeller RPM to control the oil flow to either side of the piston in the pitch change cylinder in 3 ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, while simultaneously porting coarse oil to return. The piston will move to fine off the blades, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed which traps oil both sides of the piston, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will simultaneously allow coarse oil to be ported to one side of the piston and fine oil to drain back into the engine from the other side. The piston will move to coarsen the blade pitch, causing a decrease in RPM. A constant speed propeller must be capable of all the pitch change operations mentioned previously, as they are selected by the pilot moving the RPM lever in the cockpit. The system must also be capable of maintaining a selected RPM within its own operational limits, regardless of changes in airspeed, altitude, and engine power setting. When the constant speed unit senses that the RPM is as has been selected, the system remains in a static state. However, any change in airspeed, altitude, or engine power setting will result in a tendency to either increase RPM above or decrease RPM below the value selected. As we've seen already, a tendency for RPM to increase, an overspeed condition, will be countered by a supply of oil being fed to the coarse pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then coarsen and propeller torque will rise as a result of the increase in the blade angle of attack. Propeller torque now exceeds the engine torque and will cause the RPM to decrease back to the selected setting. As the RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the position in the pitch change mechanism immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. A tendency for the RPM to reduce, which is termed a propeller underspeed condition, must be countered by a supply of oil being fed to the fine pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then fine off and propeller torque will fall as a result of the decrease in the blade angle of attack. Propeller torque is now less than the engine torque and will cause RPM to increase back to the selected setting. As RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the piston immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. Should an engine fail in flight, its propeller control unit would sense a drop in RPM, and, in an attempt to maintain the pilot's selected RPM level, would move to the underspeed or fine pitch position. Centrifugal moments acting on the blade would cause it to rotate towards fine pitch. This would result in the propeller being put into a windmilling situation, with its pitch change piston abutting the fine pitch stop. The immediate result of this would be a very large asymmetric drag, which would yaw the aircraft violently towards the failed engine. A second possibility, if the propeller continued to windmill and drive the engine, could be a complete mechanical breakdown of the engine and even an engine fire. So, to minimize drag, and also to prevent further possible damage to the engine and the aircraft, some propellers, particularly on multi-engine aircraft, are provided with a means of turning the blades edge-on to the air flowing over them. In this edge-on position, where no aerodynamic force is generated either forwards or backwards, the propeller will cease to rotate. This action is called feathering the propeller. If the engine had actually failed, there would be no requirement to unfeather its propeller. However, propeller manufacturers usually provide an unfeathering facility, by means of which, if appropriate, an engine restart may be attempted. This may be a requirement following asymmetric flight practice. The operating principle of the propeller control unit incorporated in a feathering propeller is similar to that previously discussed, in that the unit contains an oil pump to boost oil pressure delivered from the engine or reduction gearbox, and a hydromechanical governor for RPM control. There is, however, the addition of a feathering mechanism, the operation of which will be discussed progressively throughout the lesson. Control units with feathering mechanisms may be found on both turboprop or reciprocating aero engines. Dependent on the manufacturer and type of propeller system, the controller may be known as a propeller governor, a constant speed unit, CSU, or a propeller control unit, PCU. For the remainder of this lesson, we'll refer to the unit as the propeller control unit, or PCU. The controls available to the pilot are, again, dependent on type. Most spark ignition piston engines, and many turboprop engines, are equipped with a twin-lever cockpit arrangement, whereby the pilot has separate engine power and propeller control levers. In this arrangement, propeller feathering can be manually achieved by moving the propeller control lever to the feather position, or, on some aircraft, by means of a separate feather lever. Some turboprop engines utilize a single lever arrangement, whereby the pilot is provided with a power lever only. In this arrangement, propeller pitch, RPM, and engine fuel flow, power, are simultaneously adjusted. Feathering may be achieved by moving the engine high-pressure fuel cock to the feather position. New generation reciprocating engines equipped with Full Authority Digital Engine Control, or FADEC, also use a single lever arrangement, whereby the pilot selects the required power setting and the propeller pitch angle is controlled either electronically by an electronic engine control unit or by a hydromechanical control unit. This diagram illustrates that the propeller control unit may contain a number of components which are additional to the basic constant speed system that we discussed earlier. The feathering mechanism provides a means of manually lifting the landed valve to the overspeed or coarse pitch condition when the appropriate control is moved to the feather position. The actions required to feather a propeller are dependent on the type of engine and propeller combination and the type of aircraft they are installed in. For single-acting propellers, this normally involves moving the propeller condition lever, or RPM lever, to the feather position. Moving the appropriate lever to the feather position mechanically lifts the landed valve against the speeder spring to its highest position, thereby simulating an exaggerated overspeed condition. The landed valve will remain in this position until the feathering control is moved back to its normal position. Any oil in the pitch change cylinder can now drain away, allowing the spring or gas pressure, assisted by counterweights, to move the piston onto the feathering stop. To unfeather the propeller, the speeder spring tension is released by moving the propeller control lever to a position comparable to that of the serviceable engine, which of course is running at normal operating RPM. This moves the landed valve down and connects the reserve oil pressure line to the fine pitch side of the propeller pitch change cylinder. A reserve of oil pressure may be supplied by means of an accumulator, which is charged continuously during normal operation. By activating a release valve, Oil pressure from the accumulator is directed to move the pitch change piston to fine pitch. Alternatively, some systems may utilize an electrically operated unfeathering pump, or on some smaller systems, the engine may require motoring over on the starter to build up sufficient oil pressure. Once the propeller blades have moved away from the feathered position, the propeller will start to windmill, and as long as the engine has fuel and ignition, it should start. When an engine, which is fitted with a single acting propeller, is shut down after flight, the propeller should be at the fully fine pitch position. There is a considerable quantity of oil trapped under pressure on the fine pitch side of the piston in the pitch change cylinder, which is holding the propeller in the fully fine position. This oil pressure is being opposed by the force of the feathering spring. After engine shutdown, the trapped pressure will gradually leak away past the landed valve in the constant speed unit. As this trapped hydraulic pressure leaks away, the feathering spring is able to slowly push the propeller blades towards the fully feathered position. While this condition would be acceptable to a turboprop with a free power turbine, it would result in an unacceptably high loading on the starter motor of a piston engine or direct coupled turboprop. So, to prevent the feathering spring pushing the blades all the way to the feathered position, on those engines where a feathered propeller would cause stress on startup, centrifugal latch pins are incorporated in the pitch change mechanism. The latch pins are held disengaged by centrifugal force while the engine is running. As the engine RPM reduces, small springs behind the latch pins overcome centrifugal force, and they are allowed into contact with the piston mechanism. Typically, the value of the RPM at which the latch pins become engaged is around 650 to 700. After engine shutdown, the latch pins engage with a groove in the piston mechanism, which locks the piston. This prevents it from being pushed beyond a predetermined blade angle, and further into the feathered position by the feathering spring. When the engine is started and RPM increases, centrifugal force will disengage the latch pins. Fine pitch oil will quickly build up and hold the propeller against the fine pitch stop. Note that if a propeller-engine combination does have a centrifugal latch mechanism fitted, it may become impossible to feather the propeller of that engine once its RPM has fallen below the latch setting value. This is because once they are engaged, the latch pins can prevent the piston being moved any further by the feathering spring. It is thus extremely important to complete the feathering drill before the RPM decays below this figure. Double-acting propellers do not have springs or gas pressure to assist in changing propeller pitch. Thus, all of the actuation, both to fine and coarse pitch, must be hydraulic. Engine or reduction gearbox oil is once again used as the hydraulic medium for this purpose. The inset diagram of a dry sump oil tank, which you may remember was used previously in the lesson on engine lubrication, illustrates how a protected source of feathering oil is provided. The oil pressure required for feathering the propeller is generated by an electrically driven pump, which may be activated by a feathering button in the cockpit. With the exception of operating the feathering pump, the basic control selection for feathering the propeller remains the same. That is, selection of the propeller control or condition lever, operation of a separate feathering lever, or, on some turboprop systems, moving the HP fuel cock to the feather position. For the purposes of this lesson, we'll consider that we are feathering a propeller which has twin lever control. The propeller control lever is brought back through the fully coarse position to the feather position. Alternatively, where fitted, the propeller feathering lever is operated. This action lifts the landed valve in the propeller control unit upwards, thereby connecting the feathering pump oil line to the coarse pitch side of the pitch change piston, and allowing oil to drain from the fine pitch side of the pitch change piston. The feathering button in the cockpit is pushed in, energizing the feathering pump solenoid relay to supply the feathering pump. It also energizes the holding coil, which keeps the feathering button depressed for the time being. Feathering oil now passes through the ports of the landed valve, pushing the pitch change piston so that it moves into contact with the feathering stop. Oil pressure will now build up within the system, eventually operating a pressure-operated cutout switch, which will interrupt the supply to the feathering button hold-in coil. This causes the feathering button to release, which terminates the supply to the feathering pump solenoid relay, which in turn breaks the supply to the feathering pump. If the propeller is allowed to windmill, the forces generated will cause it to try to unfeather itself. Moving the propeller blades a few degrees below the feathered position will cause the propeller to rotate, and centrifugal turning moments will tend to move the blades towards a finer pitch. This will cause the propeller to rotate faster, until it comes under the control of the propeller control unit. The propeller control lever of the unit being unfeathered should be placed in line with that of the operating engine or engines, and where fitted, the feathering lever should be reset. This allows the speeder spring to push the landed valve down. It also helps to minimize the yaw which will inevitably accompany the effect of unfeathering. Pressure oil can now be directed to one side of the pitch change mechanism to move the piston towards a finer pitch, and coarse pitch oil will be allowed to drain from the other side as it does so. The feathering button should now be pressed. This starts the feathering pump running, which will supply the pressure oil to the pitch change mechanism to move the blades away from the feathered position towards fine. Once the propeller starts windmilling, the feathering button should be pulled out. Pulling out the feathering button overcomes the holding coil. When the contacts of the feathering button are opened, they break the supply to the solenoid relay, the contacts of which are supplying the feathering pump. Thus the feathering pump stops. The rest of the restart drill is accomplished in accordance with the aircraft operating manual. To reduce the workload on the pilot in the event of an engine failure, some propellers are equipped with an auto-feather system. The system is normally active during takeoff and cruise conditions only. For example, on a turbojet engine, with the high-pressure fuel cock open and the power lever set to high power, a signal of low torque from the engine torque meter system will automatically feather the propeller. Should either of these conditions not be met, the auto-feather system will be rendered inactive. This diagram shows an auto-feather system installed on a typical double-acting propeller arrangement for a turboprop engine. It consists of an additional oil pressure line supplied from an electrically operated feathering pump to the underside of a valve lift piston in the feathering mechanism. Control over this oil pressure is provided by an electrically operated solenoid valve. In the event of an engine failure, and provided the engine controls are set to the high power configuration, a low torque signal will complete the auto-feather circuit and energize the valve lift solenoid and feathering pump. This delivers an independent supply of feathering oil to the valve lift piston, which raises the landed valve to the coarse pitch position. The high-pressure oil supplied by the feathering pump is now fed to the coarse pitch side of the pitch change piston, pushing it onto the feathering stop. As the piston moves, it displaces the fine pitch oil to return. The feathering stop is fitted within the pitch change mechanism, the position of which allows the propeller blades to take up a position edge-on to the aircraft airflow, where they will generate zero aerodynamic force in either direction. The propeller should not now windmill. The propeller control unit incorporates a flight fine pitch stop solenoid, which controls a supply of high-pressure oil to a flight fine pitch stop mechanism in the propeller pitch change cylinder. When the solenoid is energized, oil pressure is directed to withdraw the flight fine pitch stop, thereby allowing the pitch change piston to move below the flight fine position and into the beta range. When the solenoid is de-energized, oil pressure is removed, and the flight fine pitch stop is engaged by spring pressure. Use your mouse to press the repeat button, which will enable you to see the removal of the flight fine pitch stop again. Most turboprop engines are provided with a system of propeller control which is defined by alpha and beta ranges. The alpha range is used at high speed, during the takeoff run, in flight and during the initial high-speed part of the landing rollout. The alpha range is selected by moving the engine power lever to a position at or above flight idle. The beta range is used on the ground only. It's selected during the landing roll by first removing the flight fine pitch stop, or FFPS, which was previously engaged to prevent the blades moving to ground fine pitch in flight, and then moving the engine power lever to a position below the flight idle position. On systems not equipped with a hydraulic flight fine pitch stop, the power lever is moved through a flight idle detent or gate. With the propeller blades functioning within the alpha range, their pitch is controlled automatically by the propeller control unit, whilst within the beta range their pitch is controlled by the operator's movement of the engine power lever. In most aircraft, the selection of the beta range is made by movement of the flight fine pitch stop, the FFPS lever. Alternatively, in some systems the selection can be made via the condition lever, that is the RPM lever, itself. A warning light, usually blue or amber, illuminates whenever the flight fine pitch stop is disengaged. Additionally, other warning lights may be provided, which illuminate whenever the propeller blades are moved below the flight fine pitch position, that is, into the beta range. While the aircraft is taxiing, there is insufficient RPM available to bring the propeller control unit on speed, and it's therefore unable to take control. Propeller RPM is controlled by movement of the engine power lever within its range below flight idle. As power is applied for takeoff, the flight fine pitch stop lever is forced into the flight position by the action of moving the power levers to the takeoff power position. The FFPS light and/or beta lights are extinguished. As the pitch of the blades coarsens to allow the propeller to absorb the increased torque being produced by the engine, the piston in the pitch change mechanism moves into the flight pitch range, or alpha range. This allows the flight fine pitch stop to engage under spring pressure, thereby preventing the piston from moving below the flight fine pitch position. There is now sufficient RPM available to bring the propeller control unit on speed and into a controlling condition. Many turboprop aircraft, and a few high-powered piston-engined aircraft, are provided with a means to allow the operator to select a superfine pitch, or to aerodynamically reverse the pitch of their propellers, or even in some cases to do both. In the case of a superfine pitch selection, a fixed abutment stop in the pitch change cylinder allows the piston to take up a position at or near 0 degrees. This is known as a disking position, and is used for starting and initial acceleration of the engine, and for aerodynamic braking during the landing roll. Superfine pitch is commonly called ground fine pitch, and its position is several degrees finer than the finest pitch available in flight, which is called flight fine pitch. The propellers of more modern aircraft may have a much greater range of blade movement in the beta range. The range can extend from around plus 8 degrees to minus 30 degrees pitch, which is full reverse. The beta range of this type of propeller is selected in a similar manner, and at the same point in the landing run as the previously discussed system, that is, during the high-speed initial part of the landing rollout. In this case, however, the braking effect obtained from the selection of reverse pitch is much more effective than that which would result from merely the selection of ground fine pitch. With the propeller in reverse pitch, the forces on the propeller blade are as shown here in the small diagram on the right of the screen. As you can see, in reverse pitch, the forces generated by the propeller will produce a braking effect to actively decelerate the aircraft after landing. On landing, the flight fine pitch stop lever must be moved to the disengaged or ground position before the engine power lever can be moved below flight idle. On systems not equipped with the removable flight fine pitch stop, the power lever must be moved through a fixed gate or detent. On some aircraft, microswitches, which sense that the weight of the aircraft is on the wheels, ensure that this selection cannot be made in the air. Once the power levers are moved below flight idle, the propeller blades move into the ground fine pitch range, and the propeller control unit relinquishes control. Propeller RPM is now controlled by power lever movement. The forward velocity of the initial landing roll, combined with low RPM and low blade angle, produces a zero or negative angle of attack. This reverses the total reaction produced by the propeller, which acts to slow the aircraft in its landing roll. This condition is known as disking braking. Propellers which can have their pitch angle made even more negative are known as fully reversing propellers. As the power lever is moved further rearwards into the reverse pitch range, the blades move into the negative pitch position. The reversed total reaction produced now increases. This exerts increased load on the engine, so engine power is increased in order to maintain a constant RPM. The engine power and reverse airflow through the propeller is now being used to slow the aircraft down. This condition is known as power-on braking. Many multi-engined aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM differences between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers, which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. In order to reduce the amount of vibration which can damage aircraft components, and also to reduce noise harmonics which can occur on propeller-driven aircraft, the engine propeller assemblies are often provided with a means of making the RPM of each unit the same as all the others. A synchronization system will reduce the annoying harmonics which can be produced by out-of-sync propellers, and also lower noise levels significantly. Electromagnets in the head of the rotating assemblies of the propeller control units of each engine are used to generate an RPM signal. An aircraft fitted with such a synchronization system will have a designated master engine, and other engines will be specified as slave engines. The signals from the propeller control unit of the master engine and those from the slave engines are sent to a control unit where they are compared. With the synchronizing system engaged, any RPM differences between the master and slave engines will be sensed in the control unit. The control unit generates proportional, positive or negative current outputs which are sent to torque motors. The torque motors are mounted on the slave engine propeller control units in such a way that a signal indicating that the slave engine is running at a lower RPM than the master will cause the slave engine's torque motor to turn in order to fine off its propeller, thus increasing its RPM until no discrepancy exists between the slave and master engine speeds. If, on the other hand, the control unit receives a signal indicating that a slave engine is running faster than the master engine, then it will send a signal to the appropriate torque motor to coarsen off the propeller blades of that slave engine to reduce its RPM, until once again no discrepancy exists between the slave and master engine speeds. So, the torque motor rotation resets the speeder spring on the affected slave engine's propeller control unit, which will ensure that it is once again synchronized with that of the master engine. When no difference in RPM exists between the master and the slave propeller, no output is sent to the slave torque motors. A more significant improvement in noise levels can be obtained by ensuring that adjacent propeller tips are separated by some optimum angle to prevent noisy interaction between them. This interaction is at a maximum when the propeller blade tips are opposite to each other, as is shown here. The synchronization system often also incorporates a synchrophasing feature that allows the operator to phase the propellers. Phasing is a means of adjusting the position of the blades on one propeller in relation to the blades of the one adjacent to it. The ability to phase can allow the operator to move much of the propeller vibration to unoccupied sections of the aircraft, thereby reducing the annoying beat of the propellers and providing additional comfort to the passengers. The systems of some aircraft provide the pilot with a means of manually fine-tuning this angle to obtain the quietest result. The more powerful an aircraft engine becomes, the larger must be its propeller if it's to absorb the torque output of that engine. Unfortunately, if the propeller diameter is increased as a way of increasing the size of the propeller, and the engine rotates at the same speed as it did previously, the propeller blade tips would be moving at sonic or even supersonic speed. This is very inefficient as well as being noisy and potentially damaging to the blades. So, if we have to use a large diameter propeller and yet maintain its RPM to a level that will not allow the tip speed to exceed that of the speed of sound, the propeller drive speed must be reduced to a more suitable level by a reduction gear, placed in the driveline between the engine and the propeller shaft, as is this example of a Pratt & Whitney R4360 engine, which is shown as a cutaway. The parallel spur gear type of reduction gear, whilst being mechanically simple and relatively cheap to produce, takes up a lot of room at the front of the engine. This is because the axes of the gears are parallel. This system of reduction gear has been utilized mostly on V-type, inline, water-cooled engines, for example the Rolls-Royce Merlin and Griffon engines. The epicyclic reduction gear layout is quite compact and has the advantage of being a concentric layout. All of the gears rotate about the same center line. The gears themselves may be straight cut, beveled, or even helically cut. Helically cut gears are extremely efficient in the way they transfer power, and they are also very smooth and quiet in operation. They do, however, impart a degree of end thrust which has to be contained, usually through the use of thrust bearings. This end or axial thrust is proportional to the torque passing through the shaft of the gear. Axial thrust, as we'll shortly see, can be used to provide a torque indication system in a propeller reduction system. A torque meter can be provided to give the pilot information about the amount of power the aircraft engines are generating during any phase of flight. The instrument may be calibrated in units such as pounds per square inch, pounds-feet, Newton meters, brake horsepower, or any other suitable unit of power. Either electronic or hydraulic torque meter systems can be found in service. An electronic torque meter system, such as the one shown here, utilizes the angular displacement of a drive shaft, which is placed between the engine and the propeller drive. This displacement, being proportional to the transmitted power, is measured electronically, and the signal thus generated is used to drive the needle in the torque meter. This system is inherently lighter and more reliable than the hydraulic system. There are two types of hydraulic torque meter system, one which utilizes the end thrust generated by a helically cut gear, the other employs the torque reaction of a ring gear. They are both used to alter the oil pressure of the torque transmission system, which is then transmitted to the torque meter gauge on the instrument panel. This simplified diagram shows a ring gear system. When the engine is running, the pinions or planet gears are being driven around inside the stationary gear by the central engine crankshaft. The thrust reaction generated by the rotation of the pinions will try to rotate the stationary gear in the opposite direction to that of the pinions. The stationary gear is restrained by being attached to pistons fitted within cylinders that are being supplied by oil pressure, which is generated by a torque meter system pump. One of the pistons in the system partially covers a bleed hole, which, if it's uncovered, will allow oil pressure to be dumped to the engine oil return. While the engine is running, the piston in the cylinder with the bleed orifice will take up a sensitive position where the oil pressure generated by the torque meter pump just balances the thrust being generated on the stationary gear. If the engine torque increases, the piston will be driven, by rotation of the stationary ring gear, to cover more of the bleed hole. This will cause the oil pressure within the cylinders to increase until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The increase in oil pressure required to achieve this balance is indicated on the torque meter gauge as a rise in engine output torque. If engine torque decreases, the oil pressure in the cylinders will now exceed the pressure required to balance the torque output of the engine, which is acting on the stationary ring gear. As a consequence, the pistons, which were being maintained in a sensitive position by the balance between the engine torque and oil pressure, will now move to uncover more of the bleed hole. This will cause the oil pressure to decrease until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The decrease in oil pressure required to achieve this balance is indicated on the torque meter gauge as a fall in engine output torque. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends upon the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine was capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear also increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new higher value, until it's able to force the gearshaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new, lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto-feather and the water methanol injection systems. The auto-feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The checks to be carried out on a propeller after engine start and the methods used will vary from aircraft type to aircraft type, and from propeller type to propeller type. In addition to the checks which are described here, it must be remembered that there are many other checks which are carried out on propellers. Most of these checks are maintenance orientated, but nevertheless a pilot is still responsible for the pre-flight visual inspection of the propeller. The particular checks that we are about to examine are those for the single-acting propeller fitted to the Piper PA-34-200T Seneca aircraft. After engine start, the engine oil must be warmed up to the level required by the operating manual before any checks are commenced. The checks form part of the normal after start and before takeoff checks. For the sake of minimizing confusion between gauges, we, in this demonstration, will concentrate only on the left or number 1 engine. The first check is a part of the power check. The remainder forms part of the before takeoff check. Here we've highlighted the particular parts of the checklist that we are concerned with. Throttle, 1900 RPM. Be aware that you don't really want to use any more RPM than necessary. Propeller, RPM lever. Exercise. This part of the check ensures that the propeller functions correctly under the impetus of the oil pressure being fed to the pitch control mechanism. Check RPM drops when min RPM selected. Pull the propeller control lever to minimum and allow the RPM to decrease by 200 as engine oil drives the piston in the pitch control mechanism towards the course position. At this point it's not necessary to wait until the RPM falls to the absolute lowest possible value. You're only checking for the correct functioning of the propeller control system. Check. RPM returns to 1900 when max RPM selected. Return the propeller control lever to maximum RPM and check that the RPM recovers back to 1900 as the propeller blades move back towards fine pitch. Repeat. Repeat the previous 2 checks again. By doing this, you'll ensure that warmer oil is being introduced into the propeller control mechanism and the associated pipework. The warmer oil will sharpen up the propeller's response to your movement of the propeller control lever. Throttle, 1500 RPM. Moving the propeller control lever back towards the white line on the control quadrant with this power set should not elicit any RPM change at all, because the propeller is within the constant speed range. Propeller feathering. Check. Moving the propeller control lever below the white line will cause the propeller blades to move towards the feathered position and the RPM to decrease. If, as is the case with the propeller we are considering, a centrifugal latch mechanism is fitted, it's important that the RPM should not drop below 1000, because the centrifugal latches will not become engaged and the propeller will feather, which is not what we're trying to achieve in this check. Throttle. Close and set 1200 RPM. Initially the throttle lever should be closed and the slow running RPM checked at between 7 to 800 RPM. Then the throttle should be set to obtain 1200 RPM. At this RPM the engine should run smoothly and the spark plug should not oil up while you're carrying out the checks on the other engine. Propellers. Max RPM. Select the propeller control lever to the maximum RPM position. Propeller de-icing. As required. If icing conditions expected during or immediately after takeoff, select On. Check propeller de-icing ammeter. Check both alternator ammeters. If your aircraft has double-acting propellers fitted, then the checks to be carried out are much the same as those for an aircraft fitted with single-acting propellers. There will, of course, be differences in detail concerning the basic RPM settings, etc., but the object of the checks will be the same. That is, to ensure a rapid and accurate response to RPM control lever movement. As with the single-acting propeller, It's necessary, once the lubricating oil in the engine has warmed sufficiently, to exercise the pitch change mechanism. This will evacuate the cold, sluggish oil from the pitch change cylinder and purge it from the constant speed unit and the associated oil passages. Just as happened with the Seneca checks, once the oil temperature is increased, there will be an engine test procedure for the double-acting propeller, which will involve causing the pitch change piston to travel from the fine pitch stop to the feathering stop more than once. With a double-acting propeller, there is not only double the amount of actuating oil in circulation, but also an extra system to check. The correct performance of the feathering pump will have to be ascertained, along with the functioning of the pressure-operated cutout switch. This concludes the lesson on propellers. Rudolf Diesel obtained the German patent for developing the idea for the diesel engine in 1892. An early example is shown here. His objective was to create a very highly efficient engine, and he succeeded by developing an engine with a theoretical thermal efficiency of 75.6%. Gasoline engines had been invented earlier, in 1876, but at that time they were very inefficient. There are two main differences between the gasoline engine and the diesel engine. They are: firstly, while the gasoline engine takes in a mixture of gas and air, compresses it, and ignites the mixture with a spark well before top dead center, the diesel engine takes in just air, compresses it, and then injects fuel into the compressed air as the piston reaches top dead center. Thus, it's the heat of the compressed air which ignites the fuel spontaneously, rather than a spark plug. The lack of a spark ignition system in the diesel engine is a big factor in increasing its reliability. Gasoline engines generally use either carburetors, in which the air and fuel is mixed long before the air enters the cylinder, or fuel injection, in which the fuel is injected into the inlet port of each cylinder just prior to the induction stroke. Modern diesel engines, especially those used to power aircraft, use direct fuel injection, which means that the diesel fuel is injected directly into the cylinder. The injector on a diesel engine has to be able to withstand the much higher temperatures and pressures that it experiences inside the cylinder, and yet still deliver the fuel in a fine mist exactly when it's required. The second big difference between a diesel engine and a gasoline engine is in the injection process. As previously stated, most automobile gasoline engines use a fuel injection system or a carburetor, rather than direct injection. In an automobile engine, therefore, all of the air-fuel mixture is fed into the cylinder during the induction stroke, and then compressed during the compression stroke. It's this compression of the fuel-air mixture which limits the compression ratio of a gasoline engine, because if the engine compresses the mixture too much, it spontaneously detonates, which is grossly inefficient and can seriously damage the health of the engine. As was stated earlier, the diesel engine compresses only the air. Thus, the compression ratio can be much higher. The higher the compression ratio, the greater the power that is generated from a given quantity of fuel, and the higher the thermal efficiency of the engine. Whereas a gasoline engine compresses the air-fuel mixture at ratios of between 8:1 to 10:1, a diesel engine, which compresses just the air, works at ratios which can range in different engines from 14:1 to as high as 28:1. The higher compression ratio of the diesel engine leads to much higher thermal efficiency. There are problems associated with starting diesel engines from cold, and because of this, some of them utilize glow plugs. Glow plugs are required because the compression achieved in a cold engine may not raise the temperature of the air high enough to ignite the fuel. The glow plug is essentially an electrically heated coil. Once the engine is warm, the glow plugs are no longer needed, and they are turned off. There are two types of glow plug in use: the metal type and the ceramic type. Metal-type glow plugs have their heating coils mounted in a heat-resistant alloy tube. Ceramic-type glow plugs, which have been employed in diesel engines since 1985, have their heater elements contained in a ceramic material, which is made of silicon nitride. Because of this fact, ceramic-type glow plugs have a greater heat resistance and durability. There are two types of fuel injection system which are used in modern light and medium-powered diesel engines. They are the direct fuel injection and the common rail fuel injection systems. We'll look at the direct fuel injection system first. Most light-duty diesel engines use an engine-driven inline pump to distribute fuel under high pressure to each of the injectors. The injectors are situated in each cylinder head. They are mechanically operated and have spring-loaded poppet valves, so they pop open and spray fuel when the fuel line pressure exceeds a certain limit, typically 4,500 psi. Electronic controls on late model injection pumps regulate injection timing, fuel mixture, and idle speed. The purpose of the fuel injection pump is to deliver an exactly metered amount of fuel under high pressure at the right time to the injector. The injector, unlike those fitted in a gasoline engine which inject the fuel into the intake manifold just before the inlet valve, injects the fuel directly into the combustion chamber, or in some cases a pre-chamber, which is connected to the cylinder. The injection system that delivers fuel to a diesel engine operates at much higher pressure than a gasoline injection system. It can be as high as 17,400 psi for a direct injection system, and up to 23,500 psi for common rail systems, compared to 35 to 90 psi for most gasoline fuel injection systems. Another function of the fuel injection pump is to regulate the timing of the fuel pulses. The timing of the fuel pulses is adjusted in response to engine RPM. Because the vane transfer pump or low-pressure feed pump, which pulls fuel from the tank to the input of the high-pressure section of the pump, is driven by the engine, at higher engine RPM, its fuel pressure output is higher. These fuel pressure changes are used to either advance or retard the timing. There is also a cold start device, which advances the idle timing manually. A mechanical governor, also fitted to the fuel injection pump, limits the maximum speed of the engine. A magnetically operated valve or solenoid opens and shuts off the fuel channel between the feed pump and the metering pump. An air inlet pressure sensor is used to determine the maximum amount of fuel delivered on injection pumps for turbocharged engines. On newer, normally aspirated engines, a similar arrangement is used for altitude compensation. The second type of fuel injection system is the common rail. The common rail fuel injection system is designed to supply constant fuel pressure to electronically controlled injectors from a shared fuel reservoir. This means that the engine fuel supply is not dependent on engine rotational speed. A common rail system is built around four basic components. Firstly, a high-pressure pump with a pressure regulator and an inlet metering valve. Secondly, a rail or fuel feed, which contains a pressurized reserve of fuel. Thirdly, injectors, which inject precise amounts of fuel into the combustion chamber as required. The injectors can be either solenoid-energized valves or operated by piezo crystal. In some circumstances, they can be actuated up to 25 times a second. Finally, an engine control unit, the brain of the system, which precisely controls the flow and timing of the injectors, as well as the rail pressure, while continuously monitoring the operating conditions of the engine. Simply explained, the term common rail refers to the single fuel feed line, from which the individual feeds for each injector are taken, on the common rail direct injection (CDI) engine. Whereas conventional direct injection diesel engines must repeatedly generate fuel pressure for each injection, in the CDI engines, The pressure is built up independently of the injection sequence in a high-pressure pump with a pressure regulator and inlet metering valve. This pressure remains permanently available in the fuel line. The common rail, which contains a pressurized reserve of fuel, is upstream of the injectors in the cylinders. It acts as an accumulator, distributing the fuel to the injectors at a constant pressure of up to 1600 bar. Mounted in the cylinder heads, fuel injectors, which are really high-speed solenoid valves, inject precise amounts of fuel into the combustion chamber as required. An electronic driver unit controls each injector's opening and closing. This procedure is regulated by the electronic engine management, the brain of the system, which separately and precisely controls the injection timing, rail pressure, and the amount of fuel injected for each cylinder. It does this by using information obtained from continuously monitoring the operating conditions of the engine. Sensor data from the camshaft and crankshaft provide the foundation for the electronic control unit to adapt the injection pressure precisely to demand. Fuel pressure generation and fuel injection are managed totally independently of each other. This factor is in itself an important advantage of common rail injection over conventional fuel injection systems. Common rail direct injection also offers distinct environmental advantages, with enhanced combustion efficiency leading to reduced exhaust emissions. The system produces quieter, smoother operation over comparable engines with either direct or indirect fuel injection. As early as 1929, the Packard Motor Company of America developed a diesel engine especially intended to power an aircraft. The inaugural flight of the aircraft engine combination, called the Stinson Detroiter, shown here, was from Detroit in Michigan State to Langley Field in the state of Virginia. The aircraft accomplished the trip at an average speed of 85 miles an hour through adverse weather. The straight line distance is 560 miles, but this aircraft, in fighting its way around and through extremely bad weather, travelled approximately 650 miles. The cost of the fuel for the flight in 1929 terms was $4.68. Automotive diesel engines in the past were less powerful than gasoline-fueled aircraft engines, and unfortunately much heavier. Since the 1980s, however, there has been a great evolutionary step forward in the development and production of aviation diesel engines. The common rail principle enables the relationship between the engine's mass and its power to become far more acceptable for aviation usage. As a consequence, due to the adoption of common rail technology and direct fuel injection, and also the use of lighter materials and turbocharger technology, diesel engines offer more advantages to the aviation industry now than they previously could. Two factors allow aircraft diesel engines to be cheaper to operate. First of all, they use the more widely available kerosene jet, Kerajet fuel, which is substantially less expensive than aviation gasoline, and they use considerably less of it. A light aircraft powered by two of these diesel engines can carry 4 passengers at speeds up to 231 miles per hour, while consuming only 1 gallon for every 19 miles travelled. If the engines are set to give maximum economy, then 42 miles to each gallon of fuel in still air can be obtained. That's approximately 9¼ miles to each litre of diesel. This gives diesel-engined aircraft a substantially increased range for a comparable volume of tankage. Secondly, aircraft diesel engines are much more durable than gasoline aircraft engines, so time between overhauls is much greater. Aircraft diesel engines are also safer than gasoline aircraft engines in operation, because of the reduced fire and explosion risk from using Kerajet fuel, and the fact that they use the compression ignition principle. An additional advantage put forward by the promoters of the engine used in the Stinson Detroiter was that it caused negligible radio interference. Of course, this comment was made in the days of fairly primitive airborne radio equipment and very poor interference suppression. However, the fact that compression ignition is used in the diesel engine is still a great advantage. The complications, which are a consequence of having twin magneto-ignition systems, as are fitted to normal gasoline aircraft engines, are removed. There are several different types of aircraft diesel engine presently in production. Amongst these are the Centurion 1.7, shown here, is made by Telit Aircraft Engines, who are based in Liechtenstein. They took a four-cylinder engine, which was first used by Mercedes, and totally re-engineered it for use in aircraft. All of the critical parts of the engine were redesigned by Telit and are now manufactured by them. It's the first modern diesel engine to be fitted to a certified airframe and scheduled for production. The manufacturers say that the engine reduces the cost of flying by 70% compared to gasoline-powered aircraft, based on fuel prices in Germany. Total operating costs for a diesel engine over its lifetime are projected to be an order of magnitude less than that of comparative gasoline-powered engines. The Centurion 1.7 is a liquid-cooled, turbocharged, four-cylinder, four-valve inline engine with common rail fuel injection. It develops 135 horsepower and 302.4 pounds-foot of torque. Displacement is 1.68 litres, and it has a compression ratio of 18:1. One of the aircraft to which it's fitted is the Diamond Star DA-40 aircraft, manufactured by Diamond Aircraft Industries. Although rated at only 135 horsepower, the Centurion 1.7 can replace more powerful gasoline engines because it provides more static thrust. Static thrust is that force which is produced when the throttle is advanced. It's a function of engine torque, gear reduction to the propeller, and the pitch of the blades. The Marine Renault's MR200 is now certified and flying in production aircraft in Europe. It's already being fitted to a Cicata TB20, similar to the one shown here, and is available for installation in several American aircraft types. Lycoming's four-cylinder, horizontally opposed, turbocharged, four-stroke air-cooled diesel engine is rated at 205 horsepower. This engine has been refined from an existing design which was originally developed in Italy and is now owned by Detroit Diesel. Delta Hawk Incorporated is currently testing a two-stroke turbo and supercharged, intercooled, four-cylinder, 200 horsepower diesel engine with the cylinders in a 90-degree V configuration. The V-cylinder configuration can be more compact and lighter than opposed configurations. Basic diesel engine operation is as follows. Initially, air is introduced into the cylinder as the piston moves down on the induction stroke. The air is now compressed in the combustion chamber as the crankshaft moves to top dead center. No fuel is yet injected. The compression ratio of the diesel engine is much higher than that of its gasoline equivalent, between 18 or 28:1, as opposed to 10:1 in high-performance automotive engines. Thus, the extremely high compression causes the air temperature to rise above the flash point of the fuel. When the fuel is then introduced in the combustion chamber, it mixes with the highly compressed and very hot air and combusts spontaneously. The pressure generated by the expansion of the gases as the mixture burns pushes the piston down. The connecting rod transfers the linear energy thus induced to the crankshaft, which translates it into rotary energy. Finally, in a similar manner to the gasoline piston engine, the exhaust valve opens and the piston drives the exhaust gas from the cylinder, and the cycle starts again. In contrast to the gasoline engine, the power output of the diesel engine is actually controlled by the amount of fuel that's introduced into the combustion chamber, while the amount of air remains constant. In the gasoline engine, both the amount of air and the amount of fuel are changed in response to throttle position. The amount of fuel being further altered by the position of the mixture control lever. The mixture control lever of the gasoline engine is required to maintain a balance between the amount of fuel and air being allowed into the combustion chamber in order that a reasonable fuel consumption can be maintained while still keeping the spectre of detonation at bay. Because the fuel is not injected into a diesel engine until the actual required moment of combustion, detonation in this type of engine is not a problem. Diesel engines do not usually operate at the stoichiometric ratio. The stoichiometric ratio is the air-fuel ratio in an engine where all of the fuel and all of the oxygen is burnt completely. If there is more air than is required, a gasoline engine will run weak. If there is more fuel than is required, then the gasoline engine will run rich. Diesel engines always run on a weak mixture, the actual mixture strength depending on the power setting. In the gasoline engine, airflow into the engine is choked by the throttle valve at all times that the engine is not operating at full throttle, which limits its efficiency. With no throttle valve, the diesel engine's intake is fully open all the time, resulting in a much higher efficiency. Most aircraft diesel engines will use regular Kerrojet fuel, Jet A, which is a light cut of diesel fuel. Jet A is not a very good lubricant, a problem which has to be especially addressed in the fuel pumps used on gas turbine engines. The fuel pumps used on aircraft diesel engines are no exception. They have to be specially developed for use with Jet A. Although anti-icing additives are used in Jet A, they may not be included in some of the other fuels which can be used in the aviation diesel engine. There is a question, which is still unresolved at the time of writing, as to whether or not to allow anti-icing additives to be used in these other fuels. Anti-icing additives would overcome a tendency which kerosene-like fuels have to absorb more water than does aviation gasoline, but the use of these additives is being curtailed in some countries for environmental reasons. The ability of the fuel to flow in extremely low temperature conditions must also be ensured, and new requirements regarding cetane number must be specified for kerosene jet fuels, which is currently unspecified. The cetane number is a measure of the ignition quality of a diesel fuel. It's often mistaken as a measure of fuel quality. The cetane number is actually a measure of a fuel's ignition delay. This is the time period between the start of injection and start of combustion of the fuel. In a particular diesel engine, higher cetane fuels will have shorter ignition delay periods than lower cetane fuels. Using the appropriate cetane-rated fuel in a diesel engine is critical to developing the power of that engine. Use the mouse to click on the Inject buttons on the screen to get an idea of the difference in ignition delay when using fuels with either a low or a high cetane number. This concludes the lesson on diesel engines.